Hello, everyone. It's good to see you all here, and hello, everyone online. My name is Maureen Hassel. I'm the Director of MSHA, and I'd like to welcome you all today to the 6th Dust and Respiratory Health Forum. It's a real pleasure to be hosting this today. So thank you all for coming and attending online. We've got quite a good only at UQ. We've just got a test happening, a fire alarm test happening here in the room. So we'll just wait for that to pass. It's going to work. We might move on to the next. Oh no, we'll wait for that. Okay. Okay, thank you for your patience with that. We move on to the next slide. I'd like to open the forum by acknowledging country. So the University of Queensland acknowledges the traditional owners and their custodianships on the lands in which we meet, both here at UQ and around the world online. We pay our respects to their ancestors and their descendants who continue cultural, spiritual connections to country. We recognise their valuable contributions to Australia and global society. Okay, so we have a couple of people in the room who are hosting. Nikky, Libby, if we have the real deal, follow their instructions, okay? So follow them in order to evacuate. All right, so moving on to the next slide. So before we get going with the exciting agenda that we have today, I'd firstly like to thank our sponsors, Resources, Safety and Health Queensland, who's represented by you today, Kerry, and Breathe Safe. So where's our Breathe Safe representative? There we are. So thank you very much for sponsoring this forum. It's a very important topic and a very important forum. And I'm the Director of MSHA. And one of the things I foresee with all the changes that are projected in order, the move to critical minerals, the transition of energies, the change in workforces, I think the understanding and the prevention of dust and doing that proactively is a really important topic that will take a collective for us to tackle so we don't keep getting into the situations that we've currently got now in Australia with the stone bench tops. So it's great to see you all here. I hope you enjoy the day. I'd like to thank, in addition to the sponsors, Nikky for organising, and Alana, who's out at the front desk, and also the chairs of the different sessions, Kerry, Libby, and who's the third? Graham, where's Graham? Oh, hello, you're behind my screen. So thank you very much for your support, and I hope you enjoy your day. And I'm going to hand over to the first chair, Kerry, to get us started on the real content.
Good morning, everyone. It's a privilege to be here today to chair the first session. It's my privilege to introduce some fantastic speakers to you. The first of which is Professor Robert Cohen from the University of Illinois in Chicago. Professor Cohen, who is affectionately known by many people in this room as Dr. Bob. So Dr. Bob is a clinical professor of environmental and occupational health sciences at the University of Illinois School of Public Health. He is also Professor of Medicine and Director of the Occupational Lung Disease Program at Northwestern University. His major research interests are occupational lung disease, particularly for mineral dust exposed workers. Dr. Bob is the Principal Investigator on the Black Lung Centre of Excellence, as well as the Black Lung Clinics Program. He also serves as the medical director for the National Coalition of Black Lung and Respiratory Disease, the organisation of federally funded black lung clinics. Dr. Bob will be presenting to us today the new US MSHA proposed silica rule, why we need it, and will it do the job? So please join me in welcoming Dr. Bob.
Thank you, Carrie, and I hope everybody can hear me. It's a wonderful pleasure to be here again. I've been at every one of these 6 dust forums, and I think it's been a great venue and a great discussion. And I'm looking forward to this again today. So we'll talk a little bit today. First of all, my disclosures of I have no conflict of interest in my mind, but these are the organizations that fund the work that we do. And today's talk, we'll talk about the latest data on the resurgence of pneumoconiosis in the United States. We'll also talk about evidence that silica is a driving factor of this resurgent disease. And I'll use that to introduce the new proposed MSHA silica rule and talk about some of the strengths and weaknesses of that rule and also compare it with some of the Queensland regulations. So some of the data that we really first got to, got to look at was really from the surveillance program of active coal mine workers that's conducted by the US National Institute for Occupational Safety and Health based in Morgantown, West Virginia. One of the things that we first noticed was looking at that X-ray program that there was clusters of rapidly progressive disease, miners who had their X-rays taken while they were working, and we found out that 1/3 of them had rapidly progressive disease where their pneumoconiosis on X-rays had progressed by at least one subcategory, and that there were large numbers of people with PMF. 41 in this particular article. This came out in 2005. And what we saw was that there were hotspots of this disease that were located in Central Appalachia, which is Virginia, this tail of Virginia, West Virginia, and then Eastern Kentucky. And that these cases were much higher, and the rapidly progressive cases were much higher in this area than the rest of the country. And this is the rest of the country. This is where we work here in Illinois, and we get miners from the Illinois basin. The other thing that information that we got from the surveillance program of active coal miners throughout the country was that there was an increase in the numbers of miners that had positive X-rays, not rapidly progressive per se, but people that had, when they went in for their surveillance, had X-rays that were showing an increase in the percentage of miners that had positive X-rays. So you can see here that 10% of the miners throughout the entire country by the time we got to around 2014, had positive chest X-rays for pneumoconiosis, and that was driven by tenure. Those with 25 or more years of tenure had that high rate. And then as you had less exposure in the mines, you had less disease. But really concerning, again, was this problem in Central Appalachia, where 1 out of 5 miners, 20%, had a positive chest X-ray. And these are active working coal miners. The rest of the United States was much better, but we still saw a resurgence. This is not what we wanted to see. We passed our dust control regulations in 1970, and we saw a nice decline in these rates, but then something happened at the end of the 20th century where we saw resurgent disease. And even more concerning, when we looked at these folks who were active working coal miners who were coming in for their regular chest X-rays, was the number of these miners that had the most severe form of the disease, progressive massive fibrosis. That's when you have a scar in your lungs that's bigger than a centimeter. And we don't expect to see anybody with that disease. And after 1970, those rates went down with a little blip due to case finding in the 80s. But really, by the end of the 20th century, those rates had declined quite a bit. But 3.5% of the miners that were in this program by 2014 were found to have PMF, and this is in Central Appalachia. And that's very, very concerning. We don't want to see this disease, and we certainly didn't want to see it increasing. So at that time, from 2009 to 2016, during the Obama administration, the US Mine Safety Health Administration had a campaign to end black lung, and they were working on developing new coal dust regulations to try to lower the exposure limits and the way that dust was sampled in the US mines in order to do something about this resurgent disease. And so that was a huge initiative led by then Assistant Secretary for MSHA, Joe Main. They were successful at the end of the Obama administration of passing new MSHA dust rules for coal mine dust. They decided that the old rule where it only sampled miners during 8 hours, even if they worked longer shifts, should be changed, and it required sampling during the entire shift. They also required that mine operators operate at least 80% of their average production during the last 30 shifts, because there were some mine operators that would reduce production when sampling took place in order to reduce the dust levels and make things look better than they actually were. So this was intended to reflect more real life conditions that the miners were facing. We also reduced our exposure limit, our permissible exposure limit at that time in 2016 to 1.5 milligrams per meter cubed. Prior to that, from 1973 or so until 2016, it was 2 milligrams per meter cubed. But there was no change to the way that MSHA regulated silica in the mines at that time. The new rule also allowed in the United States the use of the continuous personal dust monitor, so that miners could have real-time feedback on the conditions, and they could make immediate changes in the process or in their ventilation or whatever was needed to reduce the levels of dust if they were high. At that time, they added additional medical monitoring to the NIOSH Coal Workers Health Surveillance Program. Prior to this, there was only a few folks that were getting lung function testing, those that participated by participating with our mobile van unit. But at this point, in 2016, they required spirometry testing for everybody. So all miners that were participating in the Coal Workers Health Surveillance Program not only got x-rays, but they did get spirometry lung function testing. As I mentioned before, we didn't have a specific permissible exposure limit for silica, and there was no provision for rapid silica monitoring. The continuous personal dust monitor was great. It gave us total respirable dust, but it didn't tell us the percentage of silica or the mass concentration of silica. So miners didn't really know what was the composition of the dust that they were being exposed to. So what's happened since 2016? We were really excited at that time. We thought we had great new regulations, and we thought we were on the road to really preventing this disease, and certainly preventing the most severe form of the disease. But what's happened is that we've identified many more cases of severe disease, and we have a lot of evidence now that silica is a huge problem, that regulating coal dust exposure alone isn't enough, and that silica needs to be addressed directly. So I showed you this graph earlier. This is the one from 2014, which reflected a little bit earlier data. And this is 3.5%. And I tried to line it up with the most recent data or more recent data that showed that that increase in PMF cases in Central Appalachia continued to increase. And so this was is a real problem that the PMF cases were still worsening. We also had, after the 2016 dust rules were enacted, we had case reports of clusters of people with progressive massive fibrosis from some of our black lung clinics in the country. In Eastern Kentucky, there was a report of 60 patients with progressive massive fibrosis. And this is, again, a disease that we expect never to see. But this one clinic, one radiology clinic, saw 60 patients. Then in 2018, a report from 3 other clinics, this time in southwestern Virginia, that little tip of Virginia that sits underneath West Virginia. These 3 clinics had a total of 416 cases of PMF that were reported, which again is a striking number of this most severe form of coal workers pneumoconiosis. Our group, together with colleagues at NIOSH, just submitted this research letter to the Journal of the American Medical Association, showing an update on those numbers after that 2017 report. And there were 650 cases from those same 3 clinics between 2017 and 2023. And we also decided to use data from all of the black lung clinics in the United States, which University of Illinois now has the role as a Black Lung Center of Excellence and Black Lung Data and Resource Center of collecting the data for the entire country. And we saw 526 cases from the rest of the United States. So this one clinic had more cases than the rest of the United States, but still 526 cases of progressive massive fibrosis is alarming. And that is up through June of 2023. And you can see that the vast majority of these cases, even from the rest of the United States, were still from Central Appalachia, but outside of that one particular clinic. And significant numbers of these cases had the largest opacities, category C. And interestingly, they had R-type opacities on X-ray, which I'll talk about. That's a type of opacity that we associate with silica exposure. So this epidemic of severe disease is continuing. Our group also decided to look at the numbers of cases in the Black Lung Benefits Program in the United States. So these individual clinics were sentinel events and were very alarming, but we worked with the United States Department of Labor Black Lung Clinics, Black Lung Benefits Program to get all of the claims data and information on folks that had applied for Black Lung benefits in that program. And alarmingly, when we looked at the data from 1996 through 2016, we found nearly 2,474 cases of PMF. And these were cases that were adjudicated and finalized to have PMF. And the percentage of people who were filing claims that had PMF was rising. And the inflection point for this, when things started to go get bad, was around 1996 or so. So we saw that at the end of the late 20th century, we were getting increases, and these increases were continuing in many ways of measuring that data. And just to show you what an individual case looks like, this is one of the cases of severe progressive massive fibrosis. You can see on this chest x-ray, which have nice black lungs, this huge mass of scar tissue, another huge mass of scar tissue on the left side with a lot of nodularity and other scars. So this is a disabling disease that, again, we should not be seeing, but we should be preventing. So as we saw this, we saw that the coal dust rule wasn't preventing this. Granted, there hasn't been a lot of time since the rule was instituted, but we're very concerned based on a number of signals that silica is driving this resurgent epidemic that we see to be continuing. In coal mines, as you all probably know, there can be significant strata of rock above and below the coal seam that we cut as we extract coal. And it's very possible with good modern prep plant technology to separate coal from rock, in, even if there's very high percentages of rock. So we can take that rock with impunity, which we think tends to generate more silica exposure in the coal mine dust, in the mine atmosphere. This is a picture of a longwall, and you can see the longwall shear moving along. It's got water sprays, but this is the coal seam, and then above the seam, we see rock. And so again, these machines are powerful. They can cut through rock just as easily as they can cut through coal, and they can generate a large volume and a significant concentration of silica in the dust that's in the mines. Also, there are many jobs in the mines that by their nature generate silica. Pinners, or roof bolters as we call them, people that are pinning the tops and the sides of mines, people that are driving shafts, driving overcasts, and going through fault lines also can mine through large quantities of rock that has high percentages of silica. That toxic dust that's likely 20 times more toxic than coal dust. So the evidence for silica driving this resurgent disease is radiographic, pathologic. We have mineralogy and dust level data. The X-ray data use the notion of these R opacities on X-rays. These round opacities that are between 3 and 10 millimeters in diameter have been associated with silica exposure. And we looked at the X-rays of miners coming from that epicenter of the resurgent disease, Kentucky, Virginia, and West Virginia. We saw that there was a significant percentage of R-type opacities when compared to the rest of the country that wasn't having the same levels of resurgence. And this is data from 1980 through 2008, where we saw over the 80s, 90s, and then 2000s, an increase in the percentage of X-rays that had these round 3 to 10 millimeter opacities. So this was from published in 2010. This was revisited again in 2018 and published in 2019, and that's continued. So we're seeing, again, evidence that the problem hasn't been taken care of, that the problem is continuing to occur. And there's a six-fold increase from the 1980s now through the 2010s, heading up towards 2018 when this was published. So that's X-ray evidence, but it's indirect. The next kind of evidence, if you want to get something more direct, we knew that these R opacities were associated with silica, but we wanted to look at the pathology, what's going on in the lungs of these miners. And this is an explanted lung from a miner that underwent transplant. And we can see it looks like a huge, dense mass of black scar tissue and lots of round nodules. But the lung pathology actually showed features that were associated with silica and silicosis. And so we have looked at the lung pathology in a number of different ways, and I'll just go through just to show you that this has been very carefully studied now. That first lung that I showed you was from a case report where we showed 13 miners with rapidly progressive disease had silica and silicates identified in their lung tissue, just looking at polarized light microscopy and the pathology. Then I will show you a little bit more about this study that we just published last year. And then what we also did is we took a look at the NIOSH coworkers autopsy study, and my colleague, Dr. Leonard Goh, and our group looked at a shift in the type of pathology that we saw in the PMF in these miners, where it went from a cold type of PMF where the scars mainly had black pigment to the pink rounded scars of silica over time. And we saw that there was an increase in the pathological type of progressive massive fibrosis of miners in the United States. And then we also saw a number of features that were seen in the lungs of these miners. And we just published this, just came out online a week or two ago, the pathologic findings in severe coworkers pneumoconiosis in Archives of Pathology. And I'd recommend that those of you that are interested in lung pathology look at this, and we identified a number of features that are unique to the pathology of this rapidly progressive and severe disease. And we also have used other methods of characterizing the particulate using quantitative microscopy in miners with severe disease. So this one article that looked at the pathology, I wanted to show you a couple of things from it. We compared modern miners to historical miners. We happen to have lung tissue from miners that was drawn from the NIOSH autopsy study, which had miners who passed away starting as early as 1970. And what we saw was that that silica type of PMF increased in contemporary miners. 57% of miners had that type in their autopsies or their pathology specimens, compared to only 18% historically. And in Central Appalachia, it was a little bit more pronounced. We saw a reduction in the coal type of scars, which we would expect in coal miners, but there was really more the silica type and not so much the coal macules, which historically were more than 90% of the pathological lesions, but now fell to 60% in contemporary miners. But the pathological features of alveolar proteinosis, mineral dust alveolar proteinosis, which is classic for silica, was much more common in the miners that were modern miners of whom we had pathology features. And if you read that Archives of Pathology paper, you'll see lots of pictures of what these pathological features look like. So that was the pathological evidence, and I'll just mention a little bit about the mineralogy, but Dr. Emily Sarver will be talking quite a bit about some of the new techniques for looking at the mineralogy of what's going on in the lungs of these miners. We look under scanning electron microscopy, and this is a manual technique. Dr. Sarver will give you some information on an automated technique they're developing. And we basically manually counted up the particles and identified each one as to what type of particle it was. And what we saw in this study, looking at the particulate, was that contemporary miners had a greater percentage of silica and a greater particle concentration of silica. So we had really the smoking gun that we could see that silica was an important feature in modern miners who had this very severe disease compared to historical cases who had severe disease, but it wasn't driven by these changes of silica, and it didn't have the particulate that we saw here. So what's happened with the dust levels in the United States? The data that we have is taken from MSHA compliance dust sampling. And this is data from Brent Doney and colleagues that they published showing that the mean for total dust levels of respirable coal mine dust had been declining in the United States, and that's very helpful. And the rest of the United States actually had higher levels than the epidemic in Central Appalachia. But the percent of samples that exceeded the PEL for quartz percentage was higher in Central Appalachia. And when you look at the percent of quartz in dust samples from those states that have this severe epidemic of disease, you can see a significantly higher percentage of quartz in those samples compared to the rest of the United States. And this is going data that was published in 2019. Our group at University of Illinois, Dr. Yuan Xiao and Dr. Go, just analyzed and submitted this paper in the last week or so to the American Journal of Public Health, analyzing compliance samples from 1982 through 2021, almost 331,000 respirable quartz samples from over 5,000 US underground mines. And they compared that to data of Central Appalachia to the rest of the United States. And in this case, they didn't just average it over the region. They took mean mine level respirable quartz percentages and mass concentrations, and they analyzed that based on the area. And they found a number of very, very interesting things. One, that obviously we confirmed what Donnie and colleagues saw, was that Central Appalachian mines had higher mean mine level respirable quartz levels. But we tried to understand something about the ecology of those mines. What was happening in those mines that resulted in, or that was associated with the higher quartz levels? Well, they found that smaller mine size, which generally means that there's less capital investment, perhaps, less money available for control, engineering controls and other methods, smaller mine size was associated with higher mean quartz levels. Location in Central Appalachia, as we've already mentioned. Lack of a mine safety committee was a very interesting thing. MSHA collects data on whether or not a mine has a safety committee. And that may be indicative of union mines versus non-union, or just the attention to safety. But that was associated with, the lack of those committees was associated with higher levels. And interestingly, we proved or associated in this that thinner coal seams were predictive of higher respirable quartz. There's data from in MSHA's data sets on the height of the coal seams, and we were able to show that if they were thinner, implying the need to take more rock above and below the seam, it predicted higher respirable crystalline silica concentrations. So this kind of information may help guide MSHA in terms of enforcing and looking carefully at whether or not a mine might be at risk for high silica exposures. And counties with the largest numbers of workers at risk were, again, predominantly in Central Appalachia. And here's data from this paper showing the geometric mean percent quartz, and you can see Central Appalachia was significantly higher than non-Central Appalachia. Over time, that concentration remained pretty high. And then the mean mass concentration has fallen, but Central Appalachia was higher than non-Central Appalachia. So we've got a problem with silica. It's causing, we think we have a lot of evidence, both radiologic and pathologic and mineralogic and dust measurements that silica is a problem. And MSHA is about 50 years late in promulgating a new silica rule. NIOSH recommended a 50 microgram per meter cubed rule back in 1974. In 96, the Secretary of Labor had a new campaign talking about silica. It's not just dust. OSHA proposed a rule in 2012 and passed the 50 microgram rule in 2016. And then we'll talk about what's happening with the MSHA rule. In 2019, towards the end of the Trump administration, MSHA put out an RFA saying that, an RFI, request for information, saying that they wanted to get some information about the possibility of proposing a new silica rule. And that was in the summer through October of 2019. In 2020, the Office of the Inspector General for the US Department of Labor did a very in-depth report, and they concluded that MSHA needs to improve efforts to protect coal miners from respirable crystalline silica. And this was published in November of 2020. They said MSHA's silica exposure limit, which was part of a formula for total respirable dust, was out of date. That MSHA can't issue fines for excessive silica exposure because it's tied to that total respirable dust formula, and their protocols are likely too infrequent to be sufficiently protective. only quarterly underground and on the surface biannually. The American Thoracic Society and our Black Lung clinics responded saying that in that request for information, they should not rely on respirators to protect miners. That's not sufficient. We recommended the 50 microgram rule. We thought it'd be important to have aggressive and frequent sampling and sampling all mine activities, not just coal production, but also sampling high risk development activities and high risk occupations, and then increasing surveillance. Well, nothing happened after that. There was some testimony before Congress, but it wasn't until this past summer, July of 23, that MSHA actually formulated a proposed rule with language and put it out there for public comment and for public hearings. The proposed new MSHA rule that we're excited, it does propose a 50 microgram standard for coal and for metal, non-metal mines, which is the same as what you refer to minerals, mines, and quarries. It requires for the first time medical surveillance of mineral mines and quarry workers, including an exam with a licensed physician or provider, chest x-ray with a B read and spirometry. They wanted that on hire and then every 3 years mandatory, and then the first 3 years mandatory, and then a voluntary exam every 5 years. And it's based on the operator sampling and defining what the baseline levels are. And if it's more than 25 micrograms or 0.025 milligrams, then that would require further sampling and further action. It also allowed the operators to use industry data that would show that miners might not be at risk, or a second baseline sample. And if both samples are below baseline, no routine sampling beyond that was necessary. And it gives discretion to operators whether that further sampling is indicated. And if it's greater than the action level, only one quarterly sample is required, as opposed to in coal mines, 15 samples. It also doesn't require sampling of designated occupations or areas. And it does require sampling during typical mining. The MSHA proposed rule says that if your levels are greater than the action level of 25, the operator should sample every 3 months and make sure that it's not going any higher. And if it's not greater than the action level, there should be a qualitative review of the mining process and see if things are getting worse or not based on the qualitative analysis of what's happening. But there are no specified penalties or thresholds for citations. And the results of the sampling is done by private labs who are not required to send the data to MSHA, which is of some concern. It also allows the use of PPE in certain conditions where engineering controls are being developed or implemented, or if it's, quote, necessary. So that's also of concern to many of the folks that are working with miners, whether or not operators might say that PPE is necessary and not take aggressive and quick action to institute the engineering controls. There's no provision in the rule for end of shift or any type of real-time or near to real-time sampling, and it allows the use of older gravimetric technologies. So if we look at the surveillance in the proposed rule and we compare it to Queensland, just to give you an overview, the PELs are finally going to be equivalent to the rest of the world, 0.05 milligrams per meter cubed all across the board for coal and metal, non-metal, just as you have it in Queensland. In Queensland, you have an inhalable dust standard. We do not for metal, non-metal, or for coal. And so that is something that I think is something that we should look at. The initial medical surveillance is mandatory and then 3 years and includes for coal a chest x-ray and spirometry, but there's no exam by a doctor. In metal, non-metal, they are going to require an exam. In Queensland, you have a mandatory on hire exam, chest x-ray, and spirometry. Ongoing surveillance is a big difference between the US and Australia, at least in Queensland. It's voluntary in the United States, but mandatory in Queensland. You now have central data collection. We only have central data collection for coal, and the proposed rule does not consider central or mandate central data collection for metal, non-metal, which is another problem. We won't be able to analyze the data and see what's happening. NIOSH certifies its chest x-ray and spirometry sites Metal, non-metal miners can go wherever the operator sends them, and there's no certification process. RSHQ certifies providers for X-rays and exams in Queensland. And then the sampling in the United States, it's going to be for coal, it'll continue as it is with some MSHA sampling and some operator sampling of designated occupations, but in metal, non-metal, only if you have greater than the action level, it's going to only be quarterly and only one sample, only done by the operator. There's a lot of concern in the US that operator sampling may not be accurate, and there's been cases of inaccuracy and in some cases, fraudulent sampling. In Queensland, you have your sampling is a complex protocol based on the baseline levels, and you have increasing sampling depending on how close you are to the occupational exposure limits. And in coal, it's mandatory quarterly sampling for certain similar exposure groups, but it's done by operator or operator hired industrial hygienists. So the sampling in the US, having it all done by operators is a concern in our country, and that has been an area of debate as this proposed rule is going forward. We hope to see a final rule in the spring, and we'll see how that actually turns out. So in conclusion, we have a lot of areas of concern, but we're making progress. We think that radiology, pathology, mineralogy, and dust sampling indicates silica is a big problem, and especially in Central Appalachia. The new rule, we think, is an important step. We have our exposure limits in line with global standards. Sampling relies heavily on operator samples, and surveillance is improved but has weaknesses. We think that Queensland dust controls monitoring and medical surveillance has greatly improved and is really leading the world in many ways, especially since 2016. So I'd like to thank our collaborators internationally, and that's our little team, and I'm open to any questions.
Thank you very much, Dr. Bob, for a very interesting presentation. It certainly makes me proud to be a Queenslander as well when you look at those comparisons. So we're going to open it up. We've got a couple of minutes for questions before we have to let Dr. Bob go. It is quite late in Chicago at the moment. So happy to open it up to the floor or anybody online. We will have someone who can read out questions online as well. So please feel free while you've got the opportunity with Dr. Bob. We've just got a question coming up at the front, Dr. Bob.
Bob, it's Graham Edwards, consultant physician in occupational environmental medicine. Nice to see you again. What I was asking, in Queensland, have you come across from your connections any evidence that the size of the coal seam is also seems to be related to the incidence of the black lung and coal mine related diseases in Queensland?
That's a great question, Graham. We are in the process of working closely with RSHQ and the University of Queensland and WorkCover and OIR in getting a look at the data all across the surveillance, the Coal Mine Workers Health Scheme data, and we don't quite have a lot of data yet on mineral mines and quarries and trying to look at that. But I'm not aware that that's been looked at yet. We'd love to look at it. The seams that I've seen in Queensland personally are massive. I hadn't seen anything that those large seams since in the United States. So I don't know that there's a lot of thin seam mining. We're still mining seams that are as low as 28 inches, 40, up to 40 inches. I don't know that there's in Queensland seams that are quite that thin. But it'd be very interesting to take a look at the data as when we get that research project going. And I think we're nearly there to getting that project started.
I'd certainly encourage that informal conversation I had with Katrina Newbigin before her passing, is that she was seeing that in the radiology. So I would encourage.
Right, and I think we'd love to look at the, we'd like to look at that, the prevalence of these R-type opacities as well. I think that's a good indirect indicator of silica exposure, and we can look at that and see if there are any areas geographically in Queensland, looking at the coal seams and seeing if that, even if people don't have severe disease, if there's an increase in R opacities, that would be of great interest, and then correlating that back with some of the sampling data.
Yeah, and this is Nikki. So as part of that OIR project that Bob mentioned, I've also previously done some characterization work of some of the coal mines. So while it may not necessarily be thin seam, it's more inner burdens in what we have because they are massive seams. And we do have data from at least some of them to tell us what the silica and the aluminosilicates that are in them.
Okay, we have time for one more question if anybody has something for Dr. Bob. We'll just see. if
There
there's
may be
anything
something on online.
online. Have we got Kelly for the online questions? Thank you. Microphone. Thank you.
We've got a question from Rod McDonald, just asking about, because the medical surveillance program is voluntary in the US, what sort of participation rates do you see? And how does this compare to Queensland where it's mandatory?
The rates that we see are somewhere between 30 and 40%. We actually linked people that applied for black lung later and then to see if they'd ever participated, and it was also quite low, well below 50%. So it's a big concern, and we've been trying to deal with it. I think there's a lot of fear on the part of miners if they participate, one, that they might be found to have disease, and two, that there may be retribution or they might get fired. And so that's something that we're really struggling with. So I think that the workers in the mandatory program is better from a scientific and protection point of view, as long as the workers are feeling safe that if they participate, they'll be taken care of. But it's low, and that's a problem.
Thanks, Bob. There's another question that Brando is asking or saying that they're increasingly finding ILO B reader services difficult to access. Is there any issues with NIOSH certified radiology standards of reading in the US?
We've been concerned because the new silica rules mandated B reading, and so we've just got the new test. We actually administered it in Australia. It's an easier test, higher pass rates. And we are able to administer that test internationally. So we are dealing with that. A lot of our B readers are old and their eyes are fading. So we are recruiting younger folks to do it. But it's definitely an issue we have to actively recruit. And the new exam and the new training, I think, is making it easier. It's not quite as onerous as the previous one. And that's only been out for a year or so now, the new exam.
Kelly, I think we have time for one more question, and then we'll have to move to our next speaker.
That's tough because we've got heaps of questions online.
I'll try to answer them, and I'll try to answer some in the chat after
that'd be
we finish.
Great, Bob, if you could. Deborah Glass is asking, do you think that the technology used for extraction, example use of die cutting, affects silica exposure?
I don't know about die cutting in general, but I think modern mechanical mining technologies with this powerful equipment, I think, is able to generate and pulverize rock very easily and generate larger mass quantities of respirable dust that contains silica. It may be a question we can ask Dr. Sarver as a mining engineer next, but I think that the modern technologies have increased production beautifully, but they've also increased dust production and perhaps more respirable dust.
Fantastic. Thanks, Dr. Bob. And it would be much appreciated if you could answer some of those questions in the chats as well. So if everybody could please join me now in thanking Dr. Bob for his time. So it's now my pleasure to introduce our next speaker, which is Associate Professor Emily Sarver from Virginia Tech. You've seen many of her papers up on the screen in Dr. Bob's presentation. So Emily is an associate professor in the Department of Mining and Minerals Engineering, an adjunct faculty in the Department of Civil and Environmental Engineering at Virginia Tech. Her primary research interests include monitoring, characterization, and abatement of respirable dust and diesel particulates. Over the past decade, she has led or has contributed to numerous projects in this area, collaborating with industry partners, government, and researchers in occupational medicine and health sciences. Dr. Sarver is currently investigating temporal trends in respirable dust characteristics in US coal mines, the range of respirable silica particle types in mines, and the effects of various dust controls on dust particle size and constituents. Her presentation is in situ analysis of dust in lung tissue using scanning electron microscopy. Can you please join me in welcoming Dr. Emily Sarver?
Hello, can you hear me okay?
We can hear you, Emily.
Oh, you can. Okay, great. Okay, let me click off of that. Okay, so hopefully you can see slides and you can hear me all right now. So it's great to be with you. I think the last couple of times I presented at this forum, it was on characterization of dust in mines. And so I'm really excited to share with you today some of the more recent work that we've been doing about trying to characterize dust actually in lung tissue. So I note that, on my slides, it says it's November the 2nd. It's still November the 1st here. So I'm going to consider
Emily,
myself.
I'm terribly sorry. I'm going to interrupt. We're just not seeing your slides on the screen at the moment.
Oh, you're not? Oh, goodness.
Sorry, we can see your presenter view, but not your. There.
Is this better or should I?
No, that's the same. Maybe just exit share screen and try again.
Let's try that again. I'm so sorry.
Or just. Yeah, that's better. Awesome.
Perfect.
Thank you.
I'm sorry. I think I had that trouble the last time I presented at this forum. So, hopefully you can see everything now, and I'm going to talk with you about some in situ work that we're doing in lung tissue. So just some acknowledgements for you. This research has been funded by the Alpha Foundation for the Improvement of Mine Safety and Health, and also by CDC NIOSH. And I have no other financial disclosures to report to you tonight in relation to this work. The work is credited to numerous team members, including Dr. Chidem Kelesh, who recently left Virginia Tech, but is still working with us on some research. Heather Lowers at the United States Geological Survey, who's collected some of the data that I'll show you tonight as well. Carlene Kuhl and Jeremy Hua and Lauren Zelbaran and Cecile Rose from National Jewish Health, Leonard Go, Kirsten Alberg, and of course, Dr. Cohen from the University of Illinois at Chicago, and Francis Green at the University of Calgary. And the views I'll express here are those of myself and the research team, and not necessarily our sponsors or industry partners. So of course, Bob already told you that, why we're interested in doing what we're doing, and that's due to the very rapid and dramatic resurgence of particularly severe disease amongst our coal miners here in the US. And Bob gave a great intro to what I would like to talk with you about today, which is that, the surveillance data based on mostly radiology suggests that silica is really a primary culprit for disease. And so we know that silica is a problem. And the pathology indicates the same thing. So if we look under the light microscope, we start to see that over time, more of the cases of severe PMF, severe disease, appear to be associated with silica exposure, and less of those cases appear to be the classic coal type PMF or even mixed type PMF. And other recent efforts, I think Bob might have mentioned this paper from Jeremy Hua as well, starting to show that silicates are also abundant. And so it really starts to get us questioning what else is in this dust? What else is appearing in lung tissue? And how do we get a better understanding of that? And so Bob gave a great intro into, how do we actually start to look at particles? And that's what our group has been doing. So one way that we can do that is using scanning electron microscope. And scanning electron microscope is really a very useful tool if you want to look at individual particles. And the reason for that is because we get great high resolution images using the electron microscope. And we can also get the chemistry data back. So we can actually shoot an electron beam at a point on our sample, and we get data back that would indicate the chemistry. And so between those two things, we can understand things like morphology, so we can get size and shape data, but we can also get chemical data, which is really, really useful. And so the question is, well, then can you do this in lung tissue? Can you understand something about lung dust? And so there's two primary ways that folks have been trying to do this, and I'll say trying to do it for some decades. So one thing that we could do is we could take the lung tissue and we could try to recover the particles from it using something like a digestion or an ashing method, where we recover the residual particles, and we are then able to redeposit those on a suitable substrate, and use the electron microscope to actually look at those particles and sort of count them one by one and get their sizes and get their shapes. And so some things that would be, good about this method is that we can disperse particles, which means they may not interfere with each other. And so then we can start to use automated analysis. However, these types of methods, they might be more subject to losses of particles, right? Because there's quite a bit of sample preparation involved. There might be contamination issues. And so that's something that we have to deal with. Another thing is that if we take the piece of lung tissue and we digest it and then we try to get the particles back, we lose the ability to really associate where those particles were in relation to features of interest, things like histologic features of interest. And so that's a drawback to this kind of method. The other option that we might have is to actually analyze particles in situ. And so on the plus side, maybe that's less subject to losses and less subject to contamination. And there is the possibility to reference the data back to those areas of interest that might be areas particularly associated with disease or endogenous deposition. So those things might be quite helpful. However, working in tissue as a substrate is really quite challenging. And because it's so challenging, there have really been few documented attempts in the literature to try automated analysis. And the reason we would want to automate analysis is because, well, particle by particle really takes quite a bit of time. And it's also subject to user bias, right? So it matters who's analyzing the sample. So the whole question here is, well, can we automate in situ analysis? Can this actually be done? And it turns out that in our research group here at Virginia Tech, what I've been leading projects on for well over a decade now is really trying to do just that, but do it in coal mine dust. And there, we've got a much easier time of it because we can collect samples directly on the substrate that we want, and then try to analyze them. So we've been able to do a lot of automated work. But our question now has become, let's just try this. Let's see how far we can get trying to come up with an automated method for in situ lung particle analysis. And so that's what we've been working on for perhaps the past 18 months or so. So I'll present to you some of the work that we've done over that time. And I would note to you that this work is not yet published, but we are currently preparing a manuscript for Archives of Pathology and Laboratory Medicine. And so really hopeful that we'll get that submitted towards the end of the year. But it's still, at this point, a little bit of a work in progress. So our materials and methods, we started with lung tissue sections. So we had 5 micron thick sections. Those had been H&E stained and imaged under bright field microscopy before we received them. And under bright field, we had a pathologist that actually examined those tissue sections, and they were able to highlight for us where the PMF lesions were. Then after they had been annotated for us, the tissue sections were deparaffinized and they were mounted on carbon planchettes. And so we ended up with tissue sections from 10 miners. So these are coal miners that did show evidence of PMF under the bright field microscope. And from 2 of these cases, so we've just labeled them as cases 1 through 10 here for you. But for 2 of these cases, we were actually able to get 2 different tissue sections. And so we analyzed each one of the sections that we got one time. So we had 2 analyses for cases 1 and 5, and then the other ones we only had 1. We also got 4 control cases, which it turns out was really good for this work. So 4 controls, I believe these were accident victims, but they were chosen from a database that are a tissue database that based on their age and smoking histories to match with what we knew about the coal miners. And for this work, these tissue sections actually had so few particles in them that we chose to analyze each of them twice, just so that we could count more particles. And so our method, this is the automated method that we came up with. So what we have is a routine that's a regular grid of fields for analysis. Each one of these fields, we actually go in and look at about 4,000 times magnification and 15 kilovolts. And what the automated routine does is just goes from field 1 all the way up to field 69 if we have a 19 millimeter carbon planchette, and it goes up to 89 fields if we have a 25 millimeter planchette. So in each one of those fields, we use the backscatter electron detector to identify particles, and we get 50 particles per field, just going from left to right and then top to bottom in the field. And I would note most of the fields did not have more than 50 particles. So 50, covered pretty well what we saw in most of these fields across all of the tissue samples that we had to work with. In each one of those fields on each particle, we got the size and the elemental data. And then we use a normalized atomic percentage for 9 different elements, basically to as the data that we were going to use to classify the different particles. We also got high resolution images that were used to spatially reference features of interest on the bright field images to the SEM data. And so fields that were outside, you can see an example here, fields that were outside of the tissue area. We first checked those areas for contamination just to make sure that contamination was minimal in this method, which it was. And then we excluded any data from these fields outside of the tissue area. For fields within the tissue area, we sub-labeled those as either being within a PMF lesion or outside of the PMF in the lung parenchyma. And then we moved on to the challenge of particle classification. So what we found really, really quickly is that the main reason that this is much, much different than working on particles that are on an ideal substrate is that you really don't have references. So if I want to create a particle classification scheme for mine dust particles, well, I can use reference materials, but I don't have a reference for what does silica look like in lung tissue, or what does a silicate particle look like in lung tissue. I'm not sure what it should look like in lung tissue because I don't know exactly what the different biological processes might have done to that particle, or how the tissue itself interferes. And so we had to come up with another way to do this classification. So the approach that we took was to take all of the particles that we found in all 10 of the minor cases. So that was 12 tissue sections across the 10 cases. And we had just over 6,000 particles that we identified using the method I just showed you. And we used a statistical clustering approach to identify primary groups of particles based on their chemistry. So we looked at the particles in sort of the space of chemistry. So those normalized atomic percentages for the 9 elements that I showed you. And we came up with groups or clusters that approximated, different types of minerals that, in general, we would expect in these types of samples. And so you can see the table of particle classes here. Silica was a distinct class, so high in silicon, but low in the other elements of interest. We had a number of different silicate or aluminosilicate particle groups that we found. And then the blue ones, the calcium and phosphorus rich, or the silicon and aluminum, calcium and phosphorus rich, and also the sodium rich, we ended up really realizing that these are probably endogenous type particles. And then we had a few particles here and there that were iron rich or titanium rich. So a relative, we've got about 10 different classes here, but really just maybe 4 different types of particles, or 5 different types of particles in terms of what we think their primary sources are. So in addition to this, we had some data that had been previously collected by Heather Lowers at the US Geological Survey. And what Heather did is she had the same 10 cases in terms of the coal miners that we looked at, but she had a serially cut tissue section, and she used a digested approach. So she digested the tissues in bleach, then she redeposited the particles that she recovered on polycarbonate filters, and she used her own automated SEM method in order to analyze particles one by one there. And so she also came up with size and elemental data per particle, and has published this now in a publicly available data set. And so we also used that data set as sort of a reference for our work. So let's talk about some results. first of all, the in situ analysis, what we see is in some ways what we expected, which is that the particle density in the minor tissues was just enormous compared to the controls. So anywhere between 3 and about 2,000 times higher in terms of particle densities. And I just selected, just a few of the images to show you in this presentation, but you can see some of these were just chock full of particles. Really, really loaded. This is showing the distribution of particle types by case. So we have the minors here and then the controls over to the right. And what we see is that the minor tissues in most cases were really dominated by silica, which is the red portion of the bars, and then silicates, which is sort of the blue portion up to the orange in all of these bars. And so most of these cases, the primary or predominant types of dust were silica and silicates, although I would note that several of the cases exhibited a lot of endogenous particles. So things like the calcium and phosphorus rich, or the calcium and phosphorus rich that was sort of mixed with silica and aluminum. And so what we're interpreting there is that there are silicate particles or silica particles that have now been affected by the lung. The control cases, I should note, were quite variable. So we saw mostly endogenous type particles in 2 of the cases. And then in the other 2 cases, we did also have exogenous or dust particles along with the endogenous deposition. Just a little bit on particle size, we actually saw that silica appeared to be somewhat coarser or somewhat larger than most of the other particle types. And that was a bit unexpected based on the work that we've done in mines. So in mine dust, what we're actually seeing is that of the mineral particles present, silica is actually somewhat finer than some of the other particles. But that's not what we're seeing here. The silica appears to be somewhat coarser, and this is statistically significantly different. And so one question that we have, and I think what some of the data I'll show you on the next couple of slides points to, is that this is an issue of the automated method trying to do this work in situ. So we do have clustering of particles, and I think that oftentimes that means that some of the silica particles that are present get misclassified. They're actually counted as silicates or something else. I should also note that between cases, a couple of the minor cases appeared to have somewhat finer particles than other cases. And so, this is just a demonstration of the types of data that we could get using this sort of method. Some more results here. This is comparing what we found in the PMF versus non-PMF areas. So for each case, there's 2 bars. The one on the left represents what we found in the non-PMF areas. And then on the right, it shows what we found in the PMF areas. And for almost all of the cases, what we found is that the particle density, so the number of particles per area, was actually higher in the PMF areas, which makes good sense. But it was still pretty high in the non-PMF areas, and that's probably because you can see in a case like this one, here's the PMF, but I think Bob and some of the other pulmonologists in the crowd could probably say the rest of this tissue looks pretty diseased, and so we actually had high dust burdens throughout some of these tissues. We did not see any consistent trends between the particle distributions, meaning the types of particles that we saw between the PMF and non-PMF areas. And so that was perhaps a little bit surprising. When we compared our data with the digested analysis, so first I should tell you how we did that. So one thing about the digested analysis is that in addition to seeing the mineral dust particles, so silica and silicates and metals and such, it can actually see the carbonaceous particles as well. And so we had to take the digested data and group it in order to compare with our data. So everything over here on the left in yellow are particle classes that would not line up with ours. And most of the particles in those classes were interpreted as coal dust particles, which is not surprising. These are coal miner tissues. Everything in green over here on the right are things that occurred in the USGS data set, and we were able to fit them into one of our 10 classes. And so that's how we did the comparison. What you can see here is, again, we have 2 bars for every case. So the first bar, the one on the left, is for the in situ analysis that we did. And then the one on the right is for the digested analysis that we had from the USGS database. And so the digested analysis showed that silicates and silica dominated particle counts, and that was similar to what we saw. And so I think that's heartening. I think it means that we're on the right track. The digested analysis, however, did not show any, maybe 3 out of about 6,000 particles looked like they were endogenous particles. And so I think this kind of highlights a difference between the two methods. When we compare the in situ to digested results, the primary differences appear to be related to, or at least partially related to, particle clustering in the in situ analysis. So we do get clusters of particles in the in situ analysis versus dispersion, which we get more of in the digested analysis. So we've broken up those clusters of particles and now dispersed them on a new filter. And so what we're tending to see is that, clustering in situ really challenges things like silica classification. So like I said, when we have clusters of particles, it's really hard to classify each particle super accurately, and that's because it might be interfered with by other particles around it. It's also the case that when we have clustering in situ, that can limit identification of finer particles. And so it's harder to see the finer particles in situ. It's also the case that it limits identification of independent particles. So sometimes clusters could be counted as a single particle when really there's multiple particles involved. So just to kind of wrap up here with some key insights. So I think first of all, here again is this idea of doing automated particle analysis in situ. And so I think what we've shown is that, it is feasible. We can do this, and I think we can get some pretty good data out of it. I think one thing that we've learned is that we have to come up with classification approaches and interpret the data, understanding that clustering is an issue. On the other hand, understanding the clustering might be important to understanding what's going on in terms of the lung response. And so it's important to be able to reference our findings and reference what we're seeing back to the features of interest in the lung tissue. Some future work plans, we'd like to determine precision on this method. So how many fields do we need to analyze? Is what we're doing enough? And do we need more sections of tissue from the same case? We would like to apply the method to a larger set of coal miner samples and really have an emphasis on those features of interest. So we'd like to understand which features we'd like to look at and see if there's correlations in terms of the types and numbers of particles we're seeing. And then we'd also like to see, could this be applied to tissues that represent other known exposures, and what can we learn about the histology of those diseases? So with that, I hope I'm not too far over time, but I would love to have any feedback or any questions.
Thank you so much, Emily. No, you are right on time. So I might hand over to Kelly first just to see no online questions at this stage. So handing it out to the live crowd now for any questions. Very interesting presentation, Emily. Thank you. No, it looks like everybody's been wowed by that presentation, Emily, and we have no questions at this time. So we've just had one online. My apologies. Over to Kelly. Microphone coming your way.
Emily, Deb Glass is asking, could this apply to sputum samples for living miners?
That is a wonderful question and not one that I have prepared to answer, but why not? We would love to try it. In some way that maybe it's easier. I think, a lot would come down to how would we take and prepare the sample. But I think that could be awfully interesting. And I would say I would love to check the literature and see what sort of SEM analysis has been done with sputum samples and what we might make of it. But that sounds fascinating. I would love to work on it with you.
Thank you very much. We have one more question up the back.
I'm just curious as to how does this actually help impact the coal miners' health in the long run? what are we going to, how are we going to benefit from this kind of research?
That's a wonderful question. I think what I see is that, we would like to be able to develop these methods such that they are more accessible and that they could be used, number one, to understand pathology of disease so that we could understand more about, is it really just the silica in the dust that's problematic? I can tell you that each time I talk with my colleague from the US Geological Survey, she says, but why aren't we thinking about the silicates? They are everywhere. And I have the same thought when I look at mine dust samples. It's a lot of silicates and there's some silica. We're also seeing a lot of silicates in these particular tissues that we've looked at. But I think, there's the one thing where we'd like to use this to understand more about pathology of disease, because I think if we understand more about pathology, we're in a better situation to say, what should we be monitoring in the field? And then I think, we could ask Bob or some of the others. But I think there's the idea that at some point you get to something that's useful for laboratory medicine. So, not necessarily real time, but relatively quick pathology that could be done for biopsy or something like that.
Fantastic. Last call for any questions. Oh, we've got one up to the right.
Hi, I was just wondering in regards to the in situ versus the digestion method, is there any other negatives other than the inability to identify the endogenous particles that would make in situ better than digestion?
I think it's really in this idea that we'd like to understand where the particles sit in terms of which part of the tissue, and do they, these clusters that we see. So, we've done this work, we now know that they're there. Our next question is, do the clusters have any particular mineralogy associated with them? So do they always include silica particles? Things like that. So, with a digested approach, the particles disperse and you really don't know what their original sort of nature was in terms of how they occurred or what they were associated with. So I think with the in situ approach, the idea is that you get to see them as they are in the lung tissue, and maybe that's helpful in understanding what the lung response has actually been.
We have one more online question.
Deborah Yates is asking, any chance of comparing the histiopath with CT imaging?
That is a wonderful question. I don't know. And I should remind everyone that I'm an engineer, not a real doctor. So I don't know exactly the resolution of what comes out of CT. I'm just guessing here. I think is not scaled into what we could see with the SEM. So I would think that that's really an issue of where are we taking the tissue sections from? So if there's something on CT where we can really get a section that we say that corresponds to what's on the CT, then potentially, yes. At this point, we've really only thought through and tried linking up to what we can see under the bright field microscopy image, which has been analyzed by the pathologist, certainly not myself.
Fantastic. Oh, we have one more, and that's going to be our last question online.
Deborah Glass is asking, I read that bioavailable iron was a predictor of risk. So would you compare lung dust samples between affected and non-fibrotic miners?
I think that's a really great idea. And I think, at this point, we are limited by time, money, and access to tissue sections. But I think it's a really good question. In these cases, which, were selected because they had been diagnosed with PMF, we didn't find a whole lot of iron particles, but maybe that's not surprising. But if we looked at a cohort that maybe we knew had higher exposure to iron, my guess is we would find some of that. And so I think that's a really interesting question, and certainly one we would be happy to try and work with someone to look into.
That's wonderful. I think we'll call it with questions now. You can all join me in thanking actual real doctor, Dr. Emily Sarver. Thanks, Emily. So I'm now going to introduce our final speaker for session one, a dear colleague of mine, Mr. Evan Pengelly from Resources, Safety and Health Queensland's Health Surveillance Unit. So since 2016, Evan has developed and implemented reforms to the regulated health scheme for Queensland's coal mine workers in response to coal workers' pneumoconiosis. In his current role as the Director of the Health Surveillance Unit, Evan oversees the health assessment process for workers under that scheme. Joining the Queensland Government in 2004, Evan has diverse experience in policy and operational areas, including responding to resources policy changes, such as balancing land access for resource development. Evan is here today to present to us mine dust lung disease among Queensland mine and quarry workers. If you can all make Evan welcome.
Thank you, Kerry. Good morning, everyone. Today, I'm going to provide an update on the mine dust lung disease cases that have been reported through to RSHQ. And this builds on the health surveillance reports that we now publish twice yearly on our website. So today, I'm going to cover off on some of the different disease profiles we're seeing amongst different groups of workers. I'll touch on the importance of looking at cumulative exposure for workers, a reminder for our site senior executives about the importance and obligations around disease reporting, and I'll finish with a reminder about some of the screening and support options that are available for current and retired miners. But first, why do we do this? Primarily, it's to inform industry and ourselves as a regulator about whether the preventative controls that are in place are working effectively. And this goes hand in hand with systems to ensure that any disease that is out there is detected early. And that ensures that those workers can access help and support as soon as possible. Some of you who were at the Safety and Health Conference would have seen a video by Steve Carson, who is a former mineral miner who has been diagnosed with disease and has kindly shared his story. And I think part of that tells that concept in his own words, and I'll play that now.
Anybody that works in the mining industry, bench top cutters, people who cut concrete. I just thought for many, many years it was just coal mining. I never thought for one moment it was in metalliferous mining. Never. It's never going to happen to me. It did. And I'm grateful that they found it.
And I want to again thank Steve for taking part in that video. So up until 30 June this year, we had 400 cases of mine dust lung disease reported through to RSHQ. And this is across all the mining and quarrying sectors. These are cases that have an occupational cause. We also receive reports of disease where there is a non-occupational cause, and they're not included in these statistics. Up until the end of October, we now have 430 cases reported through, but for today, I'll talk about these 400. You'll see there in that red line, the chronic obstructive pulmonary disease statistics, or COPD, and that is the most common disease that we're seeing reported through. We're also seeing, to a lesser extent, a number of other diseases reported through. However, this isn't the full story, and so today, throughout these slides, we'll have a look at how that differs across different groups of workers. First, though, I'll have a look at some of the recent years and the reports that have come through to us. So as you can see, last financial year, we saw the most number of cases diagnosed, 95 in total, and a little over half of those were cases of COPD. Now, COPD can have an occupational and a non-occupational occupational cause, and I think part of the increase in the number of cases that we've seen recently has been a greater awareness of that occupational exposure. In amongst those COPD cases, we've got workers who've never smoked. We've got some workers in there who have smoked, and the cause of their disease is a combination of occupational and non-occupational. But regardless of whether the disease is ultimately determined as work-related or not, all the workers who have an abnormality determined through one of the regulated screening programs does go through a clinical pathway for further investigation. And we've just updated that pathway. So it now has greater information available for doctors to help them in making that work-related determination. Looking at that data slightly differently, this is the way in which RSHQ finds out about those cases. So you can see in that light blue area, they're the former workers. So these are retired and former workers who have taken up the option for a free lung check through RSHQ. And you can see that's increased in recent years in line with the number of people taking up the program, and makes up a little more than half of those cases that we saw last year. That thin purple line that you can see there, they're cases reported through or from Queensland Health's notifiable dust disease register. And we've been receiving reports from that register for about 12 months now. Thankfully, most of the cases that we do get reported from that register, we are already aware of, and that's good. It means that the existing pathways we have are largely picking up and reporting through to us the cases of disease. The last area I wanted to point out is that maroon area at the bottom that you can see has decreased slowly in the last few years. These are current coal miners who have been diagnosed through one of their health assessments under the Coal Mine Workers Health Scheme. So these workers have had access to the current screening program for over 5 years now, and so we would expect that most of those workers will have been through at least one screening process by now. Because we have those 400 cases, we are now able to start delving down a level and just having a looking at different groups of workers. We'll do that now, and I'll start with current workers because they do represent the most recent trends. As you can see here, the majority of those current workers we see reported through are out of the coal sector. More recently, with that light blue line, you can see we're starting to see an increase in the number of reports out of mineral mines and quarries. For both the coal and MMQ lines, where we started to see an increase in the number of reports does roughly correspond to where the mandatory screening program commenced in both those sectors. This is the disease profile for those current workers. As you can see, COPD is the most common disease being diagnosed out of those current workers as well. We are still seeing some cases of pneumoconiosis, for example, silicosis there in the green. However, this is very much a tale of two sectors. We're seeing less cases reported through for coal, but steady rates amongst mineral mines and quarries. Because the majority of those workers, those current workers, are out of the coal sector, and because we receive a copy of their health assessments under the Coal Mine Workers Health Scheme, we're able to look even further into this particular group of workers. For them, as like that overall current group, COPD is the most common. However, you can see from here that reduction in the rate of pneumoconiosis we're seeing reported through. On the graph here, looking at the blue, green and black lines around coal workers pneumoconiosis, silicosis and mixed dust pneumoconiosis, you can see those lines really flattening out. Initially, we were seeing the majority of cases coming out of the underground coal mines. More recently, we've seen an increase in the number of reports coming out of the surface mines. And so now it is a little more common to actually see cases coming out of those surface mines. The increase in cases out of surface for the surface miners does roughly correspond to where we were seeing the increase in the number of COPD diagnoses. And you can really see that coming through here, where that COPD proportion is relatively higher compared to the overall group. If you contrast that with our underground miners, you can see, yes, we are still seeing an increase in COPD here. However, coal workers pneumoconiosis remains the most common disease that's being diagnosed for workers from this sector. We're also able to have a closer look at their work histories and try and understand any differences across the work categories. So across the x-axis here are those various work categories, so production and then a range of non-production roles, maintenance, construction, transport and the like. The red bars represent the proportion of those diagnosed current coal miners that are from that sector. And the blue line represents, for the workers from that sector, what's the proportion of their career they've spent in that sector on average. And straight away, you can see that the majority of cases are coming out of production roles. However, there are quite a number of cases that are coming out of those non-production categories as well, and in particular in maintenance. Now, for both production and maintenance, those workers tend to not be particularly mobile across those work categories. Around 60% never changed work category across their career. That's different when we look at those other, or the workers from those other categories. They tend to actually be quite mobile across those different categories. So construction, as I said, maintenance, transport and the like. That differentiation doesn't apply for looking at sites though. Generally, all these workers are quite mobile across sites. Only 14% stayed at the same site across their career. I think this really highlights the importance of looking at a worker's cumulative exposure, not just looking at their exposure at their site or at their current role. These are long latency diseases, and so those exposures from 10 or 15 years ago are quite relevant. Focusing in on production and maintenance for a moment, unsurprisingly, COPD is the most common disease diagnosed for workers out of both these categories. However, you are a little more likely to see a pneumoconiosis or a multiple mine dust lung disease diagnosis out of production compared to maintenance. By the way, a multiple mine dust lung disease is where a worker is diagnosed with more than one work-related condition. We're also starting to see some emerging interesting findings amongst those who haven't spent their entire history in Queensland. So for those who have spent some time working internationally, that's quite a small group, most commonly working in the UK for the international experience, and maybe up to half of their career. Around 80% of those workers have actually been diagnosed with a pneumoconiosis, which is a little higher than what we're seeing for the broader group. For those that have had experience interstate, and this is a larger group, it makes up 15% of those current coal miners. They've had quite a wide variety of experience, so it covers all the states and territories, all the mining and quarrying sectors, and it's quite in terms of length experience, quite broad as well. Majority maybe up to a quarter, but potentially up to 3/4 as well. Interestingly, for that group, the most common diagnosis is actually a multiple mine dust lung disease, and that could be either with or without a pneumoconiosis of one of those diseases diagnosed. Now, unlike for coal, we don't receive the respiratory health surveillance reports for mineral mine and quarry workers. And there's relatively, compared to coal, fewer workers that have been reported through to us. So for talking about this category, I'll be combining current and former workers together. I'll start by talking about the way in which we find out about the cases from this sector. The most common way we find out is through accepted workers' compensation claims. More recently, we've started to see an increase in the number of reports coming through other pathways, like reports from the site senior executives. However, we would have expected to see more cases coming through those pathways. So I still think we are seeing a degree of underreporting for this sector. So I do want to remind SSEs out there that you do have an obligation to report those prescribed diseases through to an inspector at RSHQ. There's now an approved form the inspector will provide you to provide additional information on those cases as well. For MMQ, the disease profile is a little different to what we were seeing in coal, still seeing COPD. However, we are still seeing a number of cases of silicosis reported through. We're also seeing a number of multiple mine dust lung disease cases reported through. However, for this group, that's generally a combination of COPD and silicosis. So it's very much those two disease types that we're seeing. This group of workers includes quarry workers. There's 12 workers in here who have only worked in quarrying. So we are seeing disease coming out of that sector as well. If you're interested in finding out any more about disease amongst mineral miners or quarry workers, you can have a look at the health surveillance reports that we publish on our website. They've got a number of case studies, including for workers out of those sectors. RSHQ continues to provide free lung checks every 5 years for life for all former and retired mine and quarry workers. As I mentioned earlier, we're seeing an increased number of disease cases coming out of this group as a result of increased uptake. These are workers who've generally had a long career and may not have had access to screening throughout that career. Through to June, we've done 780 completed assessments for those retired miners. Majority of those have had their experience in coal. As I said, that has corresponded through to an increase in the number of disease cases that have come through. Looking at their disease profile, far and away, COPD is the most common disease that we're seeing diagnosed for this group, relatively few other disease types coming through. So those retired and former workers, they can access their free lung check through a local approved provider, or they can access it through the Melbourne Health Unit, which we've partnered with Heart of Australia to deliver. That unit is on the road around regional Queensland. It's up next week in Proserpine and Mackay, and then later in December will be coming through the sunny coast. So if you do know someone who it fits in that category of being a former or retired miner, please do encourage them to make contact so that they can get their free lung check. They can do that by calling the Mine Dust Health Support Service number that's on the screen here, and I'll put it up later as well. I've mentioned our health surveillance reports that we provide on the website. We just released our most recent one. So please jump on this QR code, grab a copy of that. It's got a lot more information on what I've talked about today. Those reports at the moment are particularly focusing on mine dust lung disease, as well as some psychosocial hazards. And over time, we'll look to add some other occupational health harms into that as well. If you missed that, I'll put that QR code up again at the end. I'll finish up with a couple of reminders. First, for those in the coal sector, all coal mine worker health assessments must now be completed on Res Health. If you don't know what Res Health is, it's our new system where the employers, workers and doctors can all complete those health assessments online. We've had over 30,000 assessments completed so far on the system. I do want to thank everyone for making it such a successful transition over from the old paper-based forms. If you haven't made that transition, you need to do that now. There's a heap of information and support material on our website, or you can give our team a call and we'll give you a hand. For those that have been diagnosed with a mine dust lung disease or are just concerned about their lung health, they can call this service, the Mine Dust Health Support Service. It's a free, confidential service, and it provides information on screening options, on access to compensation pathways, and to a whole range of support options. It's available not just for the miners, but for their families as well. So again, if you know someone in that situation, please do pass this number on to them and get them to get in touch. And as I mentioned earlier, this is also the number to call to access one of those free retired miner lung checks. So I hope that you took away from today that amongst those overall 400 cases, we are seeing differences amongst different groups of workers. Reminder again about the importance of looking at cumulative exposure, and a reminder to our SSEs about those obligations for disease reporting, particularly for mineral mining quarries. That's a really important way for us to find out about cases. And finally, a reminder about those screening and support options, both for retired miner free lung screening and through the Mine Dust Health Support Service. So thank you. There's that Mine Dust Health Support Service number again, as well as that QR code if you missed it, to go through to our most recent report. Thanks.
Thanks very much, Evan. So we can open it up. We're running a little bit early now, so we've got plenty of time for questions. So I might hand over first of all to online if there's any questions. Thanks, Kelly. I'll hand you mine.
Okay, you're popular. You've got a few questions already online. So from Brando, any specific comment about Australian international workers' exposure / disease burden from other countries such as Indonesia, Mongolia or Russia?
I don't think we can provide that level of comment. The number of workers that we do have information on with international experience is quite low, and we generally don't have a lot of information about what their experience was when they were internationally. So no, unfortunately, I can't answer that.
Thank you. Rob McDonald, thanks you for your presentation, and says that he notes there are a number of lung cancer cases now being identified. What more can you say about this, and have diagnostic criteria been developed to support the identification of their work relatedness?
Yeah, so we do see a small number of lung lung cancer cases being reported through that are work-related and occupational. We have a clinical pathway in place, and that applies for all the diseases, and that's to ensure that when there is an abnormality, it's investigated, and ultimately, if there is a disease diagnosed, that there can be that determination made about whether that's work-related.
Thank you. Brianna is asking, are lung checks available for workers at coal power stations or other industries that work with coal?
That's probably a question to ask through to Office Industrial Relations, but there's probably some options available through work cover certificates and the like if they do want to go down that path.
Thank you. Shane Power is asking, I'd like to chat with you about providing lung function in areas. Oh, sorry, that's a comment for you for later. Need to read the question first. Deborah Yates is asking, could I ask what are the relative numbers of workers in Queensland between the coal mining and the MMQ sector? So number of workers in those sectors.
Yeah, there's a little more, a higher number of coal miners. So there's still a significant number of mineral miners, but they're coal miners. We're talking 30,000 odd.
Maybe we'll ask the audience while I read these other ones. You can just throw that out to the audience as well. And any other questions while Cal catches up.
I think it's the COPD prevalence is certainly increasing very sharply. So, I mean, the smoking rates are not, I mean, they're declining overall. So what do you think is the reason there? And secondly, I think, is there a support available for smoke? I mean, before they get into the mining environment to check their smoking status and also for helping them give up smoking, is there a support provided?
There's two parts there, which I think, first part I think was a question about what might be behind that increase in the number of COPD cases. I don't think that's confirmed in any way, but I know that some of the things looking into are things like dust particle size, inhalable versus respirable, and whether perhaps that's playing a role. Second question I think was about smoking, encouraging smoking cessation. So that's not under our program, but perhaps some of the individual employers and mine sites might have some programs in place there.
Go back to some online questions. Alan Williams is asking or commenting that the breakdown between interstate and international exposures was interesting. Do you also collect any data relating to potential previous exposures in other industries such as construction or tunnelling?
Sometimes we are aware that some of these miners have travelled across from another industry, and we do have some information on that. However, it's not uniform, and there's not that same data capture that's available for us as the mining regulator. So yeah, it's a bit patchy.
Yeah. So any final questions from out on the floor? We've got one at the back. Thank you.
Hi, Antoine Bailores, occupational hygienist. My understanding is that in Australia, workplace illness fatality is poorly reported, or has been until recently. Only mesothelioma was one of the illness deaths that was properly recorded. So I was wondering if there was any appetite for also looking at population-based data, like death certificates, cancer registers, and things like this, to understand to have a better understanding, I guess, of work-related death, potentially associated with silica and other diseases.
Yeah, good question. We've got some work going at the moment with Monash University, looking into pretty much exactly that question around cancer and mortality. So stay tuned.
All right, we'll have a call for one last question if there's any more online, Kelly.
No, great. That's brought us almost perfectly on time. It was remiss of me before not to mention that any of our in-person speakers today will still be available this afternoon at the conclusion of all of the sessions. So if you've got burning questions that you haven't managed to ask during this time, any of the in-person speakers should be available this afternoon as well. So we now invite you all to join us for morning tea break. For those of us that are joining online, we will resume again at 11:10. For everybody else, if you'd like to exit out the doors to the right, moving past the bathrooms, getting into the main foyer where morning tea will be served. So thank you all for your attention, and we look forward to welcoming you back at 11:10. Thank you.
Thanks. Cheers.
Welcome back. My name is Libby Humphreys. I work for the Minerals Industry Safety and Health Centre. I look after our externally facing training group. We provide training in risk management, incident investigation and safety management systems. And a little something about me, I will talk about health and safety through wet concrete. So I apologise now. I get the privilege of introducing 3 speakers going into lunch. Our first speaker is Jeff Moredock. He's online today, coming to us from Florida. Jeff Moredock is an Executive Vice President for Skyclone International. He serves as the US Technical Advisory Group Chair for ISO TC 82. He serves as ISO TC 82 Mining Convener Working Group 9 Operator Enclosures, and as an international project lead for ISO 23875 Mining Operator Enclosures, Air Quality Control Systems, and Air Quality Performance Testing. Jeff founded the International Society of Environmental Enclosure Engineers. I'm sure he's just given me a lot of words that start with the same letter. In 2012, an international not-for-profit, which is currently focused on driving global adoption of ISO 23875 as the means to protect operator lung health. Jeff is the principal private sector researcher for NIOSH's Pittsburgh Mining Research Division Smart Cab project. Jeff teaches advanced cab theory and speaks regularly on operator enclosure air quality topics. Jeff's topic with us today is air quality control systems for operator enclosures. If you could all join me to welcome Jeff this morning.
Well, thank you, Libby. I appreciate that very much. And I thank Nikky and Dr. Johnstone for putting this Dust Respiratory Health Forum together. It's much appreciated. After that introduction, you can see that I'm very passionate about the topic that we're going to be discussing today. And I thank you for the opportunity to share it with everybody here. I want to begin this presentation really kind of where we started the day when Dr. Bob Cohen was speaking to the health-related issues and the discoveries around silicosis and various types of particulate which are in the lung, which can get into the lung through mining processes or breathing respirable particulates, and then of course followed up by Emily's research, and then all the work that RSHQ is doing, and Evan's just great work to help protect the miners there in Queensland. It's quite obvious that we've got we have a body of knowledge around the problem. We know that dust exists in mining environments where we're cutting and abrading rock, and that dust is not good for the human lung. So the real question is, that's really important to know as a starting point, but that's just part of the equation. In 2018, one of the things that was brought to my attention from Technical Committee 82 Mining was a desire to look at operator enclosure air quality, which was and has historically been a contributing factor to dust in the operator's lungs in mining environments, to see what could be done there to standardize on solutions which would provide good air quality, or at least acceptable air quality for operators working in operator enclosures. And to that extent, we were empowered to develop Working Group 9 and to bring subject matter experts from around the world on this topic, many of which were industrial hygienists. And I thank all of them. Some of them may be online here today for the good work that was done in this working group. The end game here was the development of a standard which addressed the primary needs of industry around identifying the engineering controls, which would be requisite for a cab that would be able to protect the operator, and then looking at the operational integration of that cab into a mine site, and what would that look like, and how would we go about evaluating that in real time. But if we were able to take the medical evidence, which is demonstrating the problem, and combine that with a standardized solution that was demonstrated to be effective, and if that solution was and has become the consensus standard of how we go about doing this as a world of miners, then a lot of good things can be done in the context of real-time operator protection. And the goal of everything that we're doing, both in identifying the problem, the medical surveillance, and what we've done in 2375, all has the same objectives. We want to protect our miners. So this is the warp and woof of what we're doing with ISO 23875, and frankly, the focus of what we're talking about here today. What I'd like to take a couple minutes to do for those who are not familiar with the standard is just quickly review what the standard entails. I think this will be informative for you that are not aware of this. First of all, one of the unique things about the standard today is that as of August of this year, it's now Australian New Zealand standard, ISO 23875, having been adopted as a national standard by both Australia and New Zealand. And that is just, that obviously warms my heart to see that that has been the case. I think that the interesting thing about the standard is that it does create a consistent approach to designing, testing, operating, and maintaining operator enclosures with respect to operator or air quality in the operator enclosure in the mining industry. Some of the critical things about the standard: for the first time, the standard sets out specific performance requirements, such as maintaining compliant dust levels within the cab, and that is dust concentrations on an 8-hour OEL. The goal is under 25 micrograms per cubic meter. We've seen this as not only a reality, but it's a consistent outcome of the standard when it's properly applied. In addition to that, we're looking at CO2 levels in the operator enclosure, knowing that when the operator is drawing the oxygen out of the cab and expelling CO2 into the cab, we can get an imbalance there, which actually is an oxygen depletion, which results in things happening as it relates to things that look like fatigue. As far as the operator is concerned, they can create issues there. We'll talk a little bit more about that later in the presentation. And then lastly, after we've designed the cab, we have a performance testing that we do to validate that the cab is actually performing in a finished form. That is, the cab is completed, everything that needs to be done is done, and we're evaluating it in its either fully retrofitted or fully manufactured form. And then we have the delivery of the cab into the mine site. And at that point, the occupational health and safety management program at the site takes responsibility for the cab, which involves all the stakeholders there, your reliability engineers, your maintenance folks, obviously your occupational hygienists and site management are all involved in that process to ensure that the cab continues to perform and to be tested and to work to protect the operator throughout its lifetime. We're going to talk real quickly about the 5 things that the standard is looking at specifically as it relates to engineering controls and performance metrics. The first thing on the CO2 side is we want to make sure that we have adequate intake air coming into the cab continuously to dilute the CO2 that's being expelled by the operator and replacing with oxygen-rich air, ambient air. And we've set some limits on that. The goal here is to maintain CO2 in the cab at a level not more than 400 of ambient. And we have a couple of alarms associated with the CO2. One is site set and one is an absolute alarm, which is set at 2,500. For the occupational hygienists who were on the committee, they insisted it needed to be at the action level of 2,500, which is 50% of the OEL of 5,000. The second thing that we're looking at is the recirculation air efficiency. And really, we're talking about filters on both the intake air side and on the recirculation air side. And the reason for that and the importance of that is that when an operator opens the door, he brings ambient dust into the cab. When he comes into the cab, he's bringing ambient dust on his vestments. He's bringing ambient dust on his boots. If he's got mud on his boots and the mud dries, then he's got dust that is being generated just by the movement of his feet in the cab. And the question is, what is the cab doing with the dust? Is it going to continue to propagate the dust and homogenize it in the cab such that he's continuously breathing this in, or is it going to get rid of the dust? And the answer is obvious. It has to get rid of the dust. And the way we do that, there's really two ways that we do that. One of them is by pulling the air through the recirculation filter. If the recirculation filter is high efficiency, it will strip those particles out of the air first pass, so they're not reintroduced into the ventilation system and into the face of the operator, which is generally where the ventilation is pointed. And then the second way we do that is we pressurize the cab. When the cab is pressurized, it's continuously bringing in fresh air through a high efficiency intake air filter, and it's pressurizing the cab, which is forcing the air inside the cab to leave the cab through leakage points in the cab. That does two things. It keeps dust from coming into the cab through these leakage points, but it does another important thing. It pushes the dust that's in the cab out of the cab, along with the CO2 rich air that's being exchanged. So both of these filters are very important. The intake air has to come in clean, which means it needs to be a high efficiency intake air filter, and the recirculation air needs to strip the particles out. So those two things are critical path. And I would point to Queensland's success. RS20, obviously, for those who are not aware, is already mandating high efficiency recirc and fresh air or intake air filtration to very good effect. The last thing we're dealing with here is cab pressurization. We want to maintain continuous cab pressurization from the time the key is turned on. That does two things. It maintains pressure so that dust does not come in the cab when the operator is sitting there in the cab eating his lunch, listening to the radio, and he's got the key on. The cab needs to be pressurized. This keeps the dust that's ambient outside from being drawn into the cab, and it continues to maintain oxygen-rich air coming in or ambient air coming into the cab to dilute the CO2 that he's generating. That's important because when he turns on the key and goes right back to work, we don't want him to be operating with any mental deficit as a result of having high CO2 in the cab. So this says these are the four things. And lastly, we're going to monitor all of this with a real-time monitor. It's monitoring CO2 and it's monitoring cab pressurization. And as we look to the future, for those in the room who are already involved in this, the level of monitoring that's going to go on and the ability to migrate the monitor data, the sensor data out of the cab into cloud solutions and remote solutions is already here. That's not in the standard, but that is something that's very real, and it's something that's being actively worked on by many people at this point. So we have 4 tests that are done to validate that the cab is performing correctly. When we were discussing, when we were putting the standard together and having the conversation around the testing, one of the things that became abundantly obvious was that whatever testing we were going to do on a cab had to be able to be performed in the field by the site hygienist, by a reliability engineer, by a maintenance person, by whoever candidly wanted to do the test. So the testing had to be very simple. This testing, by the way, applies whether you're building a cab new as an OEM or whether you're doing retrofits out in the field. It's the same test. The first test we look at is CO2, and we evaluate the cab's ability to bring in enough intake air to moderate the CO2 at a safe level. We then do a test where we inject fog into the cab, and we see how long it takes for the dust to settle out of the cab or to be taken out of the air. And you have, just so you get an idea of what that means, we start at a level of 2,000 micrograms. It's got to go from 2,000 micrograms to 25 micrograms within 2 minutes. And what that tells us is that the system is working adequately to strip these particles out of the air when they're brought in by the operator. And then we do a simple cab pressurization test. There's a cab monitor mounted in the cab. We just validate running the cab, turning it on, and then running at fan speed, low, medium, and high, that you've got cab pressurization. And then lastly, we spray some fog into the low pressure side of the HVAC system, which immediately tells us if we have leakages that are coming after the filter, such that the particles will be coming directly into the cab, bypassing the filter. So these 4 tests when done, are very effective in demonstrating that the cab is functioning correctly and is meeting the performance objectives of the standard. For further education on this, and I think it's already been disclosed to you, I happen to be a president of this organization at this time. And while it's an international not-for-profit, we have as our focus, as one of the things we do, education around ISO 23875. I would encourage anybody that would like to know more about the certification requirements to go to the iscee.net website. You can read about it there. You can take the online course. It's very inexpensive, and it gives you an opportunity to learn a lot about the implementation aspects of the standard and gives you some very valuable templates that can be used if you're implementing the standard. I want to talk just quickly and show you some data. The study that I'm showing you was actually published in the Canadian Institute of Mining Journal, and it was presented some years ago back at the American Industrial Hygiene Association meeting in Philadelphia. But what I want to point out here is two cabs, two drilling machines running side by side, one with a factory cab air quality setup, the other one with a retrofit setup. And what's of note here, this line that you're looking at is the level of respirable dust, PM10 dust that's inside the cab. So this is the dust concentration, and you can see it's going up and down, up and down, up and down, because on a drilling machine, you've got the operators getting out and changing the drills frequently. So this was happening, and every time it happened, we had an influx of ambient dust coming in the cab. And you can see from the peaks to the valleys, these are minutes down here. It took a long time for the cab to settle the dust out. And it never did get to the red line, which is 50 micrograms, which would have been regulatory compliance. So the entire time the machine ran, it was averaging 248 micrograms. It needed to be at 50 in order to be compliant. The bottom illustration shows what happens when you apply 23875 requirements to the cab, where you're using the high efficiency fresh and recirculation filtration. And this study very clearly demonstrates the value of having the particles stripped out of the air immediately upon passing into the recirculation filter. And the key here is that over the time that this study was run, the average dust concentration was around 10 micrograms. And the silica concentration, after we were doing two tests simultaneously, this was real time, plus we were doing the standard NIOSH test with the pump and the cartridge. And when the cartridge was analyzed, it demonstrated that the silica content was less than 0.05, well, that's 0.05 micrograms. Yeah, that's right. 0.005 milligrams, or 5 micrograms. So well below the 25 microgram requirement, well within compliance, well below an action level. So this is the kind of performance that we expect to see when the cab is pressurized, when it's running high efficiency fresh and recirculation filtration. I want to talk just for a minute about one of the sidelights that came out of this, not only out of the standard, but the research leading up to the standard. So over the years, as we were doing research in the society, we found something very interesting happening, and it happened in very different ways. We had, in this instance, a wheel loader where the operator never turned on the HVAC system. No fresh air was being brought into the cab. And the black line in the middle is the CO2, and it rose to the limit of detection on my CO2 monitor at 4,000 ppm in less than an hour runtime. And that was one study. Another study here was on a Komatsu HM400, similar situation. The HVAC was running, the heater was running. These other lines are other data points, but the black line in the middle is the CO2, and it just climbed in a period of 27 minutes. It also climbed up to 4,000 ppm. So what we were seeing is a very rapid rise in CO2 concentrations. And we have another illustration of this in a Komatsu D475A bulldozer, where with that same black line, the same thing was happening here. Once again, HVAC was running, the guy was cool in the cab, but his CO2 aggregation was quite high in a relatively short period of time. I think the total time of this test was 42 minutes. So what this taught us was that CO2 was something that we needed to be looking at. Further studies were done after we got the working group together in underground mining. We can talk more about that. If anybody has any questions, we can talk about that more. We'd like to get more studies done here. And one last thing about CO2, I've been traveling the world quite a bit this year. I was down in Antofagasta, Chile, and went up into the is it Atacama up in the high desert. And it occurred to me as we were driving up to about 8,500 feet in altitude, or 3,500 meters, that all the studies that have been done, the sensors have been set up, everything has been done, assuming sea level that everything was done at sea level. So when we start gaining altitude, we lose the oxygen percentage in the air. And when this takes place, we have a completely different configuration as it relates to how much intake air needs to be coming into the cab in order to offset the CO2 which is being generated by the operator. Candidly, none of this has been studied yet. I think Dr. Robin Burgess Limerick is working on a CO2 study right now. I know we've got folks at Rio Tinto that are studying CO2, and I'm hoping that when this is all done, we're able to develop a much improved understanding of CO2 and its effects on the humans as it relates to fatigue-related issues as well as altitude issues. I'm going to talk just a moment here as it relates to the adoption of the standard. These are various companies. You all know the names that are here: Rio Tinto, Anglo American, BHP, South 32, Tech Coal, Tech Resource, Agnico Eagle, Heidelberg Cement Group, and Nevada Gold Mine Company. Each one of these companies has in some way embraced, whether that's incorporation into their corporate specification or putting out machine specifications with ISO 23875 or AS ISO 23875 incorporated into the specification. This is very encouraging as we think about how we're going to address, how we're going to get from, understanding what the problem is into actually solving it in our mine sites. It's just fantastic to have these companies actively engaging in implementing 23875, and we're very hopeful that, well, we're not hopeful, this will continue. I have no doubt of that. And as we get better and better at the implementations, we're going to see more and more of our operators in environments which are healthy for them to be operating in while they're in their machine cabs. We have some countries that have adopted the standard. So as we spoke about earlier, Australia and New Zealand have adopted it as ISO 23875 without change. It was adopted by the European Union as EN ISO 23875. It's adopted by Sweden as a country as Swedish standard, EN ISO 23875. It was put into the health legislation in Denmark in May of 22. It was adopted by Colombia, South America without change in 2022. And it's been contemplated as a part of the silica rule revision by MSHA in the United States. We've had a lot of discussions with MSHA. I know Bob talked about the MSHA reg that we're hoping is going to come out here in the spring. We had discussions with MSHA about the standard as early as August of 2019 when it was just in draft form. We did submit it to MSHA for comment, and they gave us comments on the draft. So these are some of the organizations. While it was in draft form, we submitted the draft out to a lot of different organizations, which are all stakeholders in this standard. The AIHA, a mining working group in the US, gave probably the most thorough comments on the standard. They were very active in commenting. OSHA received a copy of the draft, but they were already in rulemaking, and they would not comment on the draft because of that. MSHA had not started rulemaking. They did comment on the draft, as did NIOSH. Actually, the Pittsburgh Mining Research Division commented on the draft. And we got comments back from the AIOH, as well as from our friends at the Queensland Mine Inspectorate, which we're very grateful for, also very insightful comments. And also received comments back from members of the Earth Moving Equipment Safety Roundtable, immersed while it was in draft stage. So I would say we had, we see the importance of adoption because a standard that we invest a lot of time and energy in that does not result in anybody using it is massive waste of time for everybody that's doing it. But we could have made the other mistake too, which is not consulting with everybody while the standard was going on. And I will say that we have gone out, we went out of our way, and we'll do this again when the revision comes up in 2026 to reach out to our stakeholder groups. We have many more people who are aware of this now. I expect to have a very robust discussion around various things that we need to do to improve the standard when it comes up for revision in 2026. I would say for those in the room, anybody that is interested in that, please drop me an email. I've got a list going of those people who I want to make sure get copies of whatever the revisions are going to be. So you have an opportunity to weigh in on that when the time comes. And I would appreciate anybody's participation at that point. I have some closing thoughts here before we go to questions. And one of them is really what the standard is attempting to do is to change mining culture toward operator air quality. As I've been going to mine sites literally around the world this year, one of the things that I notice and have been told many times is that the operators are not able to plug into this or don't understand it. We've got site personnel that don't understand it. So education really remains the primary challenge to getting this fully implemented. And I will tell you, ICE is working on education as well as others are at this time. And I just would encourage everybody that has an opportunity and is willing to participate either in helping us develop education or developing education around this, that you would be an influence in your area towards getting ISO 23875 implemented. And if we do that, I believe with all my heart that this is going to become a reality in the mining world. Thank you very much. I'll take questions.
Thank you very much, Jeff. If anybody has any questions, Kelly, do you have any online?
So we have a question around the CO2 in the cabs. The person asking the question assumes that CO2 steady state happens within minutes of it being occupied and the system run. That's what they had thought, but apparently not, according to Jeff's presentation. Also, could or should the standard be extended to related uses, but not strictly mining, such as soil contamination remediation, for example, asbestos in soil, PCBs, PAHs, etc.?
Yeah, let me take the first question there on the steady state. If there's adequate intake air, and the standard talks about intake air in context of 43 cubic meters per hour, you will have a stabilized CO2. It won't go all over the place. But what you saw in those previous illustrations were cabs where there was not intake air coming into the cab, and the operator was literally depleting the O2 in the cab, and that's why you were seeing that steady rise in CO2. If there's adequate intake air, you will absolutely obtain you will get to a steady state in short order in the cab, and it will maintain itself as long as the intake air is adequate. The second thing is whether or not the standard could be applied to other industries or other cabs or other uses. The answer to that is absolutely. While it was developed by TC82 Mining, the basic physics and understanding of how cabs operate is the same. It doesn't change from an ag cab to a construction cab to a mining cab. So if you want to take 2387, apply it to another application, there's no reason in the world why it wouldn't work. Kelly, I saw another question had come in from an anonymous attendee that had some questions about the CO2 sensor.
Yes, it's a massive long question. So if you can read it, that'd be helpful.
Yeah, well, let me just paraphrase what they're asking. It has to do with why we're measuring CO2. We're measuring CO2 because we've got a very discrete CO2 sensor. The requirement of the standard is a non-dispersive infrared sensor, which uses a CO2 frequency that's very accurate in looking at the CO2. Could we have used an O2 sensor? I would say that the question is, why didn't you use an O2 sensor instead of a CO2 sensor? And I would suggest that there are good arguments on both sides of that. I would encourage this discussion is one of the discussions that I'm sure will be brought up again when we go into a revision of the standard in 2026. I'm making note of that here. And we will definitely have that conversation in the working group around, the pros and cons of doing with them. We had the discussion before and we wound up going with the CO2 sensor, but we can certainly have that conversation again.
Jeff,
Okay,
Joanna
yes.
Holland was wondering if you've published any of the data from the sampling you've done inside the cabs of personal exposure to dust.
If we publish the dust data inside the cab. Oh, this is interesting. So we have, as a part of what we've done in ICE, we have case studies that we did that we use in teaching. As it relates to many case studies which have been done and are being done as we speak, there's a lot of activity in the case study side with our occupational hygienists who are doing studies after implementations have been done, and they're getting phenomenal results. The problem with these studies are that they're specific to mine sites, and it's information that is not releasable. At least I'm not allowed to release the information. So if somebody that's in the mining industry wants to do a case study that they can release generically, that would be greatly welcome.
Thanks, Jeff. And you've got two questions, one relating to retrofitting existing cabins. Is that something that happens or is it just new machines? And then the opposite question around, is there any requirement for original equipment manufacturers to provide cabins that meet the standard?
Both excellent questions. Excellent questions. So on the retrofit side, the answer is sure. You can retrofit a cab to comply with 23875. In fact, most of the machines that are going to be done are retrofit installations, because if they started manufacturing machines today in the mining industry, as we know, because of how long it takes to get mining equipment, it's going to be a long time before you're going to see cabs, at least in mass, with 23875 compliance. Is there a requirement for the OEM to produce a 23875 compliant cab today? And the answer is yes, when it's in the machine specification. So if the mining company includes 23875 in the machine specification, then the OEMs absolutely take that seriously. I can tell you out of personal knowledge that all of the major OEMs in the mining sector are working frantically to get ISO 23875 cabs into production. So that's something they're definitely working on.
Thanks, Jeff.
Yes.
We have a question just up the back there.
Yeah, hello, Jeff. Mike Lewis here, Principal Occupational Hygienist. We actually had the gentleman from Cyclone actually present the same information at the recent chapter meeting. And the question I actually raised with them was mainly to do with the sensor configuration for the real-time monitors inside the cab. You've got the CO2, but could the standard include different sensor configurations based on the type of industry? For instance, I'd actually seen a survey where a truck cabin had actually had a filter-based system, but it was basically an open path system. It was actually drawing in products of decomposition for spontaneous combustion from spill coal heaps, and it was actually causing some immediate health effects, whether that could actually be included as an extension to the sensor system based on industry type. Yes.
And I would suggest the answer is yes. And I would tell you that when we talked earlier about the monitoring, this current sensors, the CO2 and the pressure, you're going to see dust as a part of the monitoring program. And you have the opportunity for many other sensors to be incorporated, which would be various gas sensors, along with gas filtration. So we knew when we did the standard initially that we were not covering gases, industrial gases, mining gases. Because it has its own complexities. We are working on that standard right now. If you're interested in that standard and would like to participate, we'd love to have you on the team. It's called ISO 21208. It is in process. If there's anybody in the room that would like to participate in the operational integration of gas filtration, this would be your opportunity to do that. And I would welcome you on board and walk you through how that can be made to happen as far as your participation in the working group.
As we only have Jeff for a few more minutes and he won't be here for the Q&A this afternoon because he will be sleeping. Do we have one more question? No? Well, if you'd like to put your hands together, thank Jeff very much for his time this morning.
Thank you.
So our next speaker is Peter Knott. Peter is a certified occupational hygienist and fellow of the Australian Institute of Occupational Hygienists. With over 35 years experience in the field within Australia and overseas, he is currently a principal hygienist with GCG Health Safety Hygiene. Peter has represented industry bodies in Australian standards committees for workplace atmospheres, respiratory and hearing protection. He has tertiary qualifications in chemistry, environmental health and epidemiology, and is currently a doctoral candidate in clinical epidemiology at the University of Newcastle, researching the effect of lifetime occupational exposures to chemical mixtures on selected chronic diseases. Peter comes to us today to talk to us about trends in mine dusts and implications for the future. If you could please join me in welcoming Peter.
To speak. Just a couple of things. So as said, I'm a full-time employee of GCG. We conduct a lot of this dust monitoring with mining companies throughout Australia, and the data that is involved in this presentation was was obtained from RSHQ, so it's not GCG data, and they're basically not representative of GCG's position. So you wonder why I put the GCG logo on the thing. I didn't think of that last night anyway. So what's the context of what we're doing? So basically, this work is restricted to Queensland coal, surface, underground, and CHPP data from 2010 to present, and it's in the context of this reduction of respirable crystalline silica down to an 8-hour TWA of 25 micrograms per cubic metre, and the implications that has for extended shift operations where potentially we could be looking at exposure standards of around 12 micrograms per cubic metre. All of this is prefaced against the general decrease in the dust exposures that have occurred in the Queensland coal industry over the past, particularly 5 to 7 years. And how is that lowering of dust levels combined with a lowering of an exposure standard for silica? Now, how do we reconcile those things? So the data that we got from RSHQ, basically all of the respirable dust and respirable crystalline silica exposure samples from 2010, they're all paired up. They have a unique sample identifier, a mine key and a sample date in the record. I will point out that the unique sample identification is not unique, which I found out to my chagrin, but anyhow, I had to work around that. We excluded samples that were greater than 720 minutes and less than 360 minutes. So I basically took 50% of an exposure standard, 50% of a shift up to a full shift. And we only looked at samples with respirable dust. We excluded samples that had a respirable dust concentration that was that should be around the wrong way. Respirable crystalline silica greater than the dust. So obviously someone swapped the data around. So we analysed that basically using some statistics packages that are available. So what does it tell us? So this is the data by year by mine type, so CHPP, surface and underground. The number of samples are up there, so 7,000 results for CHPP, 32,000 for surface, 22,000 for underground. The interesting point to make is that so the censoring means that they're results that have less than something less than a value, right? So if you get your results. Basically, that means that the laboratory couldn't determine if there was a quantity of silica greater than what their laboratory method just identifies. And one of the sort of, I guess, striking things that I noticed was that 2017, there was like a shelf where a lot of the results, there was a much greater degree of censoring post that. And that may or may not be related to when there was increased regulatory scrutiny of results, perhaps. How that looks in terms of the actual exposures, these are all arithmetic means in micrograms of silica. So once again, you can see that, we get to this 2017 and there is a, particularly for CHPP and underground, so this potentially could be an RS14 effect. The results aren't as significant until you get down sort of a bit later on, which could be when there was some more attention with surface mines. But I guess when we look at it, comparing what Bob was talking about with the Appalachian data, they're talking about average exposures now around about 20 micrograms of silica. We're currently at a quarter of those values now, but historically we've been at those levels that Bob was talking about earlier. There's another point to be made is that the spread of these results. So as we're getting sort of lower and lower concentrations, we're seeing a greater and greater spread. So the actual results are starting to spread out more. Now, that potentially results from two things. One is that we're getting more and more of our exposures are getting lower and lower, but we're still getting sort of those abnormal exceedances events that are occurring. Right? The other thing that happens is once you get more censoring in the results, that artificially increases the spread, because what we're doing is we're assuming that a value is between the censored result or the less than number down to 0. So once we get more and more results in that censored band, the spread essentially goes down, increases, because 0 essentially you've got an infinite numbers from the censored result down to 0. So that partially explains why we're getting some of these really quite extreme geometric standard deviations in these groups. I should add these results aren't weighted in any way by the number of samples collected from any particular mine. So there's no weighting applied to the fact that there might be a lot more samples collected at, say, a larger mine than, say, a smaller mine, something like that. So we know how much people are getting, but how much silica is in the dust? Basically, what we had to do, because there was a lot of censored values, basically just did multiple imputation, and so where there's either the respirable dust or crystalline silica value was censored, we essentially calculated a imputed value from that. And this is all the data. Basically, just had a couple of things that are of note. So this is the percentage of silica in the individual respirable dust samples. And you can see here, whoops, back. Wrong one. So you can see here that for the prep plant, there's a clear horizon below which sort of what your results are, right? So prep plant people don't get exposed to dusts that contain 50% silica in them, right? They're basically, it's run and mine coal with a bit of rock in it. They're processing that. Where you do get some higher ones, potentially that could be from rejects handling, not too sure. Similar sort of thing appears with underground, but it is certainly much more pronounced. It's up a bit higher. There's potentially much higher exposures that occur to high concentration silica dust, which could be essentially from, you know, just mining methods, stone, faults, what have you. Surface guys, it's a completely different pattern. You know, there is quite a spread evenly either side of this is the median line here, quite a spread evenly divided on either side of the median. So they can be routinely exposed to dusts which may contain 20, 30, 40% silica, which, you know, logically is probably overburden and things like that, right? So if you look at this as a bit of a summary and how things have gone over that intervening time period, what we see is the reduction in percent silica from sort of a geometric mean greater than 11% down to about 9%, and it's quite flattened off for surface operations. So that's sort of the average now, sorry, the geometric mean now. Underground and prep plants sort of had this decline to, you know, 2015, 2016, and then there's sort of this steady increase over time where we're now getting around about 7% silica in respirable dust. The other thing down the bottom, this is the geometric standard deviation of the spread, and this decrease in the underground geometric standard deviation, so the spread of the percent silica, so less people are being now exposed to sort of higher concentration silica dusts. I don't know, a couple of thoughts. Working in returns, working on, you know, tailgate side of shearers, things like that, potentially where there is more likely to be a higher concentration of rock in crystalline in the respirable dust samples. That potentially is one of the explainers for this. So what all of that information, so what does that mean for us in terms of exposure control, exposure assessment in the future? So we can do a number of things. We can sort of get more information out of the analysis that we're already doing, right? We can collect more dust maybe for existing analytical methods. So given that we're only looking at very small amounts of silica, we want, and we're going to be comparing that to a much lower exposure standard, you know, we're going to need more silica to measure. Are there any other alternative analytical methods around that have lower detection limits? Or can we use more sensitive sort of aerosol monitors and then infer sort of silica exposures from those? So how do we get more information out of the analysis that we already do? Well, like I said earlier, censored results assume that the concentration is from whatever that limit of quantitation that the lab has down to 0. So what that means is that we report a result. This one here, if it's above this limit of quantitation, it's, yeah, for example, 0.1, right? If it's below that, the lab will say, oh no, that's, you know, less than, right? And that value, like I said, goes from there all the way down, basically down to 0. What about the information that's in the middle? So the limit of quantitation is the reliable level where the laboratory can, with a certain degree of precision, tell you how much silica is in the sample. The limit of detection under the IUPAC standard conventions, the laboratory conventions, is that there is the presence of a substance is noted, but we don't know the concentration of it with a certain degree of precision, right? But typically what laboratories will use a limit of quantitation, So we could use, potentially, we could say, well, this result here, this is above here, this could be 0.1. Yep, I've got it's above my limit of quantitation. This interval means that we could say, well, I know it's less than this value, but I know that it's greater than the limit of detection. Like there's something there. I can't really tell you how much there is, but I know there's something there, definitely. Which is called interval censoring, essentially. That's currently not reported by laboratories. It's not typically part of their sort of typical analytical process. Part of the reason it's a difficult measure to handle, like a value to deal with statistically. But Bayesian statistical methods handle interval censored methods with ease. Like it doesn't really matter. So we could do that. That will give us more information about where our actual results lie. And also means that we're able to bring that geometric standard deviation in, because we're not assuming that results go all the way down to zero. We now have some confidence to say, well, actually, no, there's some of those results, they're sort of up more towards our limit, where we can quantify it, but we don't exactly know what the number is, but we know that it's sort of up on that end of the distribution. Collect more dust for analysis. There's another option. Maybe we need to rethink the standard Higgins Joule cyclone that we collect. 2.2 or 3 litres a minute. There's an option. There's a 4.2 litre respirable cyclone available in stainless steel or aluminium if you want to use it on a surface mine. Drawback is that you want to sample that for 12 hours at 4.2 litres a minute. Sample pumps that we typically use for underground work, if the battery's really, really good condition, it'll work. If the battery's not in such a good condition, you'll get lots of voids. So that's a problem. However, that cyclone does perform exceptionally well when compared to our traditional cyclones. So if you go down that track, then there are alternatives out there that will give you comparable data. So you're not existing analytical methods. Okay, so we currently use X-ray powder diffraction, so XRD, so we can extend the scan time. So just leave it in the instrument for longer, hit it with more X-rays, get more response. We can put all the dust deposit into a smaller and smaller spot potentially, but there's limitations to that. We can use different X-ray sources. We can try to lower noise through sort of different software and instrumental methods. FTIR is the other method that we use, particularly for coal. If you drop the temperature of your FTIR down, you can sort of squeeze a bit more sensitivity out, but you basically sharpen the peak up. You're talking about like using liquid nitrogen and things like that to drop the temperatures right down. Once again, you can sort of put all of your dust into a smaller deposit to try to get more concentrate. There's similar sort of spectral analysis, like software methods, to try to analyze the FTIR spectrum a bit better to resolve interferences and things like that. But really, like a lot of these techniques are known, or they're being used by the laboratories. And really what we're doing is we're sort of just squeezing out marginal improvements to get slightly better performance. So are there alternative methods out there? Is there something else? Is there another black box that we can put samples into to get a better analysis? One promising approach is called Raman spectroscopy. It's similar, but not the same as FTIR. And I won't go into the fundamentals of Raman spectroscopy, but you can Google it. But the UK Health and Safety Executive have been looking at this approach.
It is very feasible at the current performance limits of XRD and FTIR. It's capable of detecting silica polymorphs. So, quartz, cristobalite, separate those out, right? Quite effectively. There is some interference from different materials, especially iron oxide and just metallic iron is an interference. But that's not an insurmountable problem. It's eminently overcome by sample preparations like acid digestion and things like that. So for our engineered stone people, so this was some work done using using Raman spectroscopy. FTIR and XRD rely on, their sensitivities rely on particle size to a certain extent. And both of them suffer at very low particle sizes. So if you're looking for particles less than a micron in size, FTIR and XRD, it shows attenuation. So that this work showed that a comparable analysis of engineered stone samples, the response or the quantified response for XRD and FTIR actually end up with a lower result than the Raman spectroscopy method. So how that plays out for engineered stone exposures could be interesting. It is a promising alternative for them. They identified a limit of detection, or actually a limit of quantitation of around 0.2 micrograms. So a fifth of what the best performing XRD method is currently. There is an issue with putting too much dust into these things. So about 1 milligram deposit is all you can do. And in doing that work, identified some other interferences from rutile and zircon. So once again, it's not a panacea for everything, but it certainly is a much better technique. NIOSH have also been looking at Raman spectroscopy for application. And they come up with a couple of different sort of sample preparation techniques, which, when you look at it, we're getting with a 1 minute sort of analysis time in the instrument, you're looking at sort of 8.8, limits of micrograms, 0.07, 0.008 micrograms. So they are 10 times at least lower than what we're getting with current XRD, FTIR techniques. Once again, high particle load, so too much dust, not a good thing. Also, identification of interfering species in that process. But like I said, FTIR and XRD also have interferences, right? So they are not alone in being in subjecting to interferences. Some recent, or not so recent work, I guess, extended this work down to short-term samples. So they were basically doing task-based samples, 30 minutes, an hour, hour and a half, 2 hours, with low dust concentrations, less than 0.2 or 200 micrograms total, and very accurately determining crystalline silica in those task-based samples. Whoops. Can we use more sensitive aerosol monitoring? Possibly. So you could go with a hybrid sort of approach. Use a real-time aerosol monitor. They'll pick up down to a microgram, and then use some estimates of percent silica from sort of traditional sampling. You could sort of then supplement that sort of work with sort of traditional, I guess, gravimetric compliance monitoring with, high flow samplers, what have you. But that's another way potentially of dealing with this. So So the future for silica exposures in Queensland coal, well, crystalline silica exposures coming down. The percentage of silica in the dust appears to be going up in some sectors and staying constant in surface. What can we do in the short term? You know, basically we're squeezing more out of what we've already got, using, you know, real-time assessment, and then, you know, basically like a silica fudge factor. In the medium term, you know, there's potential for using some of these newer statistical techniques, interval censoring. Raman spectroscopy is sort of coming down the pipe. Whether that's, you know, it's currently not commercially available, but, you know, there are instruments quite available to be used. There's none that are being used for silica routinely. Longer term, well, yeah, we might be able to go with, you know, higher flow rate samplers, combine it with some of those other analytical methods. But really, if you want to use that sort of approach in the longer term, we're probably going to need better pumps for handling those higher flow rates over longer periods of time. So that's me. So I just want to thank RSHQ for providing that data. It was much appreciated.
Thank you, Peter. So we will just have time for one question, remembering that Peter will be back at 3:30 for Q&A at the end of the day. So if I can have, is there one question for Peter? Yep.
Alan Williams would like you to comment on the time period when SKC black plastic cyclones were not correctly sampling respirable fraction, and whether that was taken into account in your interpretation of the data. So when did we pick that up and swap, and did you take that into account?
No, I didn't. It's that data. I think the issue around sampling with SKC cyclones is historically one of those things I don't think will ever be able to be resolved. It's done. That's what it was. And tell Alan I'll see him later.
If you could please put your hands together and thank Peter. Our next speaker is Stephen Gillies. Stephen Gillies is the Director of the Occupational Health, Hygiene and Asbestos Unit at the Workplace Health and Safety Queensland, leading a small group of advisors that provide technical advice to the regulator and to industry. Stephen has a broad range of industry, consulting and government experience in occupational hygiene and public health, with a focus on protecting workers and the community from harm. His presentation title today is for the Office of Industrial Relations on the new construction or the revised construction code of practice. If you could please welcome Stephen.
Thanks for having me today. I really appreciate it. I'd just like to just flag today that the work on this code was mostly conducted by my team before I arrived at the organisation. So if you love it or you hate it, it's not my fault. But I'll do my best today to give a bit of a highlight of the code. So the code became live on the 1st of May, 2023 this year. It applies to all construction work and the manufacturing of construction elements in the construction industry. It's Australia's first silica construction code. Hopefully at the end of my presentation today, you'll have a bit of an understanding of how the code was developed, the purpose and application of the code, some of the key elements, such as triggers for health monitoring, and the use of the controls table in Appendix 4. I'd also like to give a little bit of a brief summary of my view of what the challenges are for the regulator in this space and where to from here. So the Construction Silica Code, it is a very mouthy title, so I'll just refer to it as the RCS Construction Code for the rest of my presentation. The code was not developed in isolation. As you can see from the above slide here, the code was developed in close consultation with workers, employers, unions, and technical experts across Queensland, building on international best practice to ensure silica dust is managed safely and workers are protected in the construction industry and the manufacturing of construction materials. So the above representatives here on this slide formed a steering committee, had several meetings between 2020 and 2021. The code, as I said, was developed through consultation in these meetings. Due to the broad scope of the construction industry, once a draft code was completed, a broader industry reference group was established and invited to provide written feedback on the code. The Construction Silica Code is an approved code of practice under Section 274 of the Work Health and Safety Act. It was designed to be a practical guide to achieve the standards of health and safety and welfare required under the Act and the regulation. The code incorporates all existing elements of the Act and regulation which apply to the management of RCS. In Queensland workplaces, compliance with the code is enforceable under Section 26A of the Act. However, alternatively, you can manage hazards in a different way, but they need to achieve an equivalent or higher level of safety to the code. The code outlines how the PCBU can manage risks associated with RCS at the workplace in a way that meets all of the legal requirements of the Act and Reg. So where does the code apply? The code applies to all construction work and manufacturing construction elements, regardless of where that takes place. So materials included in the code need to contain greater than 1% crystalline silica. However, they also need to have the potential to generate dust containing RCS or make RCS airborne. The definition of construction work is set down in Section 289 of the WHS regulation. This includes work such as commercial construction, residential construction, civil or tunnelling. The manufacture of construction elements applies to all materials used in the construction work, regardless of where they are manufactured is undertaken. It's not just limited to work on construction sites. So what does the code not cover? It doesn't cover the manufacture of tools or plant used in construction. It doesn't cover the engineered and natural stone benchtop industry. As many of you will know, there's a separate code of practice for that industry that was released in 2019. So any activities in quarries and mines, that's not covered. That's not our jurisdictions. That's our Resources, Safety, Health and Queensland. So what does the code classify as an RCS task? So two things are needed to be considered an RCS task. There needs to be that percentage of crystalline silica within the material that people are working with, but there also needs to be that potential that RCS is generated or it is disturbed and become airborne. So as an example, a bricklayer constructing a wall, the code does not apply. Although the material contains greater than 1% RCS, there isn't a potential for RCS to be generated. However, that same wall, if someone takes a saw to it and starts generating airborne RCS, the code then applies. So how does a construction site worker or a PCBU or a workplace find out whether the materials they're using contains greater than 1% RCS? That information is most commonly found on safety data sheets, product information labels, potentially from the importer or the supplier of the material. If that information is not available, there's also potential the material could be tested in a NATA accredited laboratory. If there's absolutely no way to find out the silica content of the material, then we are asking that PCBUs presume that the material contains greater than 1% crystalline silica. So this is the key steps within the code, and this is really what I wanted to highlight here. I don't want to take you through the entire code itself. So the key bit here is the pathway to which a PCBU can demonstrate compliance. You'll see that there's these two separate boxes. Do I have a laser pointer? I do. These two boxes here. These are this pathway here has always been the case. If you're going to introduce controls for RCS, you need to validate that those controls are effective by conducting air monitoring. That pathway still exists within the code of practice. There are some changes, but that pathway still exists. What this code provides is an option for those small and medium businesses that may not have the resources for engaging an occupational hygienist and undertaking their own air monitoring. We've given them a pathway to compliance with the control task table in Appendix 4. That task table has a list of common construction activities, and it recommends engineering controls and respiratory protection. I'll talk more about that later, but that's really what I wanted to highlight on this slide, was that this pathway here has always been the case in the existing provisions of the regs. This bit here is really what I wanted to highlight. We're giving PCBUs and businesses an opportunity to use existing data to validate the controls that we're suggesting in that control table. So this is an excerpt from Appendix 4, the controls table. As you can see, we've got someone using a portable saw over here on the left, a water-fed saw. So this is a common construction task. We've got the task on the left-hand side here, and over here we've got two different engineering control methods for that particular task. We've got an integrated water delivery system, continuously feeding water to the blade, or we've got a commercially available dust collection system. These are your two engineering controls that Appendix 4 provides you with as a means of a validated control measure. So as we move further along here, we've got the respiratory protective section. So the table acknowledges that engineering controls will not always be sufficient to reduce exposures below the workplace exposure standard. In this particular instance, you can select whether the work is conducted indoors in an enclosed space or outdoors. The respiratory protection section gives you the minimum protection factor of the RPE. I'll talk a little bit about that later. And the last column here talks about health monitoring requirements, which I've also got a slide on later. So air monitoring, when is it required? So as I said previously, when we're talking about air monitoring, we're talking about a PCBU demonstrating that they've validated their control measures. So when you're not certain on reasonable grounds that your workers are not exposed above the workplace exposure standard, then you need to undertake air monitoring to come up with your control measures and then validate that they work. We talk about certain on reasonable grounds. Within the regulation, there's currently no definition for that term. So what we've done with this code of practice is we've provided that context around certain on reasonable grounds. So if you're using a control measure, which is described in Appendix 4 of the control table, and an inspector rocks up at your workplace, you can demonstrate that you are certain on reasonable grounds that your workers are protected. Alternatively, as I described previously, you can go your own way, determine your own control measures, whatever combination of you like, obviously using the hierarchy of control. But what you need to have is statistically valid exposure data to demonstrate that your workers are protected. So the code has very prescriptive detail of what is required from occupational hygienists working with this code of practice. We're asking for similar exposure groups. We want baseline monitoring. We've got details on how reports should look and feel. We've got instructions on how samples should be analysed. All that information is now detailed in the code as a practical guide to help workplaces. Who can undertake air monitoring? The code prescribes who can undertake what work. So we're asking for a certified occupational hygienist to plan that air monitoring and determine similar exposure groups. The actual monitoring itself can be undertaken by an occupational hygiene technician. But the interpretation of those results, again, we're asking for a certified occupational hygienist to undertake that work. Health monitoring. The regulations have previously advised that where a significant risk is present for handling a hazardous chemical like RCS, then health monitoring is required. But there's been no detail on what significant risk is and how to determine that. The Code of Practice now prescribes what the regulator sees as a significant risk. And the way that we've done that is where RPE is used to protect workers from the WES. So if a worker is required to wear a respirator on more than 30 days in a year, we're using that as a trigger for significant risk. So PCBU doesn't have to wait for that 30 days to occur before they organise health monitoring. The idea is that if you've got an understanding that your workers will be required to wear respiratory protection in greater than 30 days in a year, then you can go ahead and organise that health monitoring. So challenges and next steps. Codes of practice are reviewed every 5 years. The work that was done when this work was done, the exposure standard was 0.05. There's obviously been some talk today around that reduction in that exposure standard. That task table was informed by data from OSHA with an exposure standard of 0.05. A reduction in the exposure standard means that that task table needs to be revised. So that's something that me and my team are working on at the moment. Looking for more data and the next directions for that control table. The code has been rolled out. My team have been responsible for training the inspectorate throughout Queensland. As part of the release of the code, there was an audit campaign undertaken with 200 construction sites visited by inspectors and 100 manufacturing sites where construction elements are manufactured. I'm awaiting data from those early site visits. And once we get that data, that'll inform the next steps for the regulator. So in summary, the Code of Practice applies to all construction and the manufacturing of construction elements. It commenced on the 1st of May. Construction materials to be under this code are defined as containing greater than 1% crystalline silica. The controls table gives an opportunity for small and medium-sized businesses to allocate their resources to effective control measures rather than organising their own exposure monitoring. You can go it yourself, you can go it on your own, you can use your own controls, but you need to provide statistically valid exposure monitoring. And if a risk still remains, RPE is required. And health monitoring, where there's a significant risk, which we have defined in the code. That's it from me. Thank you very much.
Thank you, Stephen. Do we have any? No, Stephen's actually run very nicely.
Catch us up.
Ahead of time. We still have 10 minutes before lunch. Sorry, if I can have a microphone down the front, please.
I've got a question up here first. It's a two-part question. Firstly, is it explicit around what the components of the health surveillance is for these people? And secondly, is there any information on how compliant we're seeing the construction industry just yet?
The second question, I don't have that data available to me. I have, from what I have seen early on, the manufacturing sites where construction elements are produced appear to be more compliant than areas of the construction industry. What we're seeing is tier one construction companies have put a lot of effort into preparing for the release of the code. Where we're going to see issues, I would suggest, is in those smaller to medium-sized businesses. And to the first part of your question around health monitoring, the code does provide details on that.
Graham Edwards, occupational physician, and involved in the drafting of the engineered stone sector code of practice. I welcome the code first and foremost. It's a major step forward. The second part of it is around the assessment of risk and what is a significant risk. And while the code defines using a respirator for greater than 30 days and 12 months, how do they decide whether or not they even need to use a respirator? Because even on 1 or 2 days, because what I've seen in general is the a lax attitude to using respiratory protection, and also in other situations using respiratory protection when they actually don't need to. So there's a challenge to actually reliably use respiratory protection even as a last resort.
Yeah, I guess I can probably add some context there. If you're using the control table within Appendix 4 and it doesn't recommend respirators after those engineering controls have been introduced, and a worker chooses to wear RPE, even if that control table doesn't suggest that it's necessary, that doesn't count towards that 30-day trigger for significant risk in the code of practice. But I do take your point regarding the challenges with RPE and for construction sites enforcing that. Obviously, we want workplaces to go through that hierarchy of control and only use RPE as a last resort.
I believe we've got one question online.
We've got a couple. They quickly appeared. First of all, there's a question around how you made the decision on the 1% content of the silica, and the person asking the question believes, is not sure though, that the GHS uses, what the globally harmonized system uses 0.1%. Why did you choose 1% for the code?
I don't know. So I'll take that on notice.
All right, take that on notice. Hamish Ray is interested in the controls table at the back. He says there was recently a paper published in the Annals of Work Exposure and Health that found elevated levels of RCS even when the OSHA controls table was used. Is there consideration of reviewing the controls table in light of that and similar data?
Yeah, absolutely. So this is obviously the OSHA data that was used to inform that control table is from a point in time. And we want, my team particularly, we want to receive data from industry and from industry groups, and we want this to be something that's consistently updated when new data emerges. So I'm certainly not suggesting that this is going to be the controls table moving forward for a significant period of time. We want new data, we want to update it, and obviously with changes in the exposure standard, that is going to, trigger revised controls in that table also.
Thanks.
We have one question just here at the front.
Yes, Keith Adam, occupational physician. Forgive me if I appear to be beating the drum for self-interest, but unless I missed something, I was very disappointed in the group of people you consulted with at the start. There didn't appear to be any occupational medicine representatives there, unless I missed something. And more importantly, when you go through the code of practice, it's very carefully specified who are appropriate people who are qualified to undertake occupational hygiene work, but there's no such specification about who ought to undertake medical assessments. And I'm sure your colleagues in the mining industry could share their experience of how important it is to make sure that people performing that work are adequately trained and experienced. It seems to be a mission in the code.
Thank you. Thanks for your feedback.
So on that note, I'll leave you all to ponder questions you would like to convey to Peter and Stephen after 3:30 for the Q&A. We should have lunch outside. Everybody's due back in the room at 1:40 for our next session of speakers. Thank you very much for your time this morning. Just a final thank you to Stephen for his presentation.
Afternoon. My name's Dr. Graham Edwards, for those who don't know or heard of me. I'm the occupational physician that brought the engineered stone silicosis to the media attention back in 2018. It was my clinic on the Gold Coast that actually started seeing the numbers and brought that to the attention of the regulators and insurers in Queensland, and subsequently to Minister Grace announcements in September 2018 that kicked off the regulatory responses to the sorry situation we had there. Punishment for my sins, I got appointed to the National Dust Diseases Task Force, and I was the lead author on the management of the guidance for doctors to manage exposure to respirable crystalline silica in general, and focusing on the engineered stone sector. I'm also a AMA under the Coal Workers Health Surveillance Scheme, a designated doctor under the other schemes run by RSHQ. And I've been asked to chair this afternoon's session to bring together both the science and the clinical aspects of what we're dealing with. So we've got an interesting panel of speakers, and I'll introduce each one. Because we do have the opportunity of a panel session at the end of the presentations, burning questions will be welcome, but you may trigger thoughts both online and through the processes of the conversation. So we've got that panel discussion at the end of today's session. So to kick off, first is Dr. Chandnee Ramkissoon, who is an early career researcher in occupational hygiene and health at the University of Adelaide. She's working with Professor Sharyn Gaskin down there, and she'll be presenting the paper this afternoon, The Role of Exposure Science in Managing Dust-Related Occupational Lung Disease, bringing together that. So Chandnee has led and managed the dust characterization projects to investigate the link between particle chemistry, the science of that, and occupational lung disease in the manufacturing and fabrication industries. She's recently been awarded the prestigious Eye Care Dust Diseases Board's postdoctoral fellowship to pursue her research in the toxicology of the new generation low silica stone products and their implications for policy change around Australia. So she's an active member of the Australian Institute of Occupational Hygienists and is an executive member of the South Australian Northern Territory branch of the Thoracic Society of Australia and New Zealand, TSANS. So welcome to Chandnee, please.
Thank you, Dr. Edwards. Good afternoon, everyone. So my name is Chandnee, and unfortunately today it will just be me presenting. Sharyn sends her apologies. So my talk today is titled The Role of Exposure Science in Preventing Occupational Lung Disease, with a particular focus on the manufacturing industry. Thank you. So before I start, I would like to acknowledge the traditional custodians of the land on which we gather today and pay my respect to the elders past, present, and emerging. So my talk today will cover briefly three topics. So I'll start with a bit of an introduction about my research team at the Adelaide Exposure Science and Health Unit at the University of Adelaide. I will then give a bit of a description of our research program that we have led in the last couple of years, applying exposure science to the prevention of occupational lung disease. And I will finally finish with some future directions. So the Adelaide Exposure Science and Health Unit is based within the School of Public Health at the University of Adelaide. It is led by Associate Professor Sharyn Gaskin and is staffed by various professionals, including occupational hygienists and exposure scientists, working across various scientific disciplines from epidemiology to toxicology to the development and evaluation of interventions. But what is exposure science? Exposure science is really the science that underpins prevention. through the identification and management of health risks from environmental and occupational hazards. Why is it important that we apply an exposure science lens to problems? Well, as exposure scientists, we really link the problem to the solution, because the approaches that we use really allow us to understand better the types of hazards that we're dealing with and their nature, which in turn allows us to implement more effective control measures to mitigate those exposures, which in turn, again, is key for disease prevention. So in the last couple of years, we've led a research program that has looked at the prevention of occupational lung disease in silica dust generating industries, in particular the manufacturing industry. And for this purpose, and given today's topic on silica, I will be focusing on the manufacturing industry in particular. There are other reasons why I'm focusing on the manufacturing industry. As you may already know, it's a multi-billion-dollar industry that has really boomed over the last couple of decades due to the rising popularity of engineered stones. Engineered stones are artificial stones. They're made by mixing together finely crushed rocks that are high in crystalline silica content with a resin matrix to form a product that really is very aesthetically pleasing, is very durable, and it's certainly quite affordable, which explains its popularity among consumers. Now, unfortunately, this popularity has also brought about a rise in occupational lung disease, so silicosis, among stone benchtop industry workers. Engineered stone-associated silicosis is progressive, it's incurable, it's often fatal, and it's impacting young workers that have been working in the industry for a short period of time only. And this is in stark contrast with historical forms of silicosis that tend to develop over a 20 to 30-year period, and which I dare say had largely been eliminated in Australia. But overall, occupational lung diseases like silicosis are entirely preventable. So it's really imperative that we understand what is causing such a severe burden of disease among this occupational group. Given their bulk composition, it might seem reasonable or perhaps even logical to associate it with the high exposures and high silica content of the stone, but it doesn't seem that these factors together quite explain the severity of the disease and the short latency period associated with this new form of silicosis. So which is where exposure science come into play. And in the last couple of years, we've set up a program to understand exactly that. We've set up programs to investigate in depth and in breadth the characterizations of the emissions generated when engineered stone products are actively processed. At the Adelaide Exposure Science and Health Unit, we are set up to generate these dust particles in a relatively realistically exposure scenario, as is designated on the schematic diagram on the left and a small picture on the right. So within an enclosed Perspex cabinet, we do zip cuts onto different stone types, and the emissions that's generated in real time are captured using conventional air samplers. And sometimes we also use some real-time monitors to understand what's happening inside the box. So in the first instance, we looked at 12 resin-based engineered stone products, and we also included some natural stones like marble and granite for comparison. And we characterized the dust particles that were emitted during those processes for their physical and chemical characteristics. So that means their particle size, their particle charge, their surface area, their morphology, their mineralogy, their resin content, and their metal elements content as well. Because engineered stone products also contain an element of resin, we also set up separate experiments to capture and identify any potential resin breakdown products in the form of volatile organic compounds. And this setup is really quite unique because up until that point, what we knew about these products were just really the bulk composition, which is high crystalline silica content and some resin. So the outcomes of this project have been published in the last year, and they are in open access journals. But if you don't have access to them, please email me directly. I'd be happy to share them. And for these reasons, I won't spend too much time on the results, but we essentially saw that engineered stone processing generates very fine particles. These particles are very high in surface area. They are in much higher surface area than dust particles generated from cutting natural stones, for example. And in the respirable fraction of these dust particles, you have very high crystalline silica content as well. They also contain some elements in the form of metals. But really quite interestingly, and we perhaps suggested this for the first time, is that there is a potential for workers to be co-exposed to different hazards during those tasks, because we also identify VOCs such as styrene and phthalic anhydride, which you may or might not know, but they are both lung irritants. It's quite well documented that occupational exposure to styrene, for example, is directly linked to respiratory problems. And phthalic anhydride is a respiratory sensitizer. So that program of work really described quite well the variability of hazards that's associated with engineered stone fabrication. So then we wanted to expand the scope of work to a scale that would allow us to then determine with statistical significance whether there was any differences of these dust exposures on lung cell experiments. And this is a project looking at the role of particle chemistry on disease pathogenesis. Now, this project was a truly collaborative venture between ourselves and biomedical researchers from the Menzies Institute for Medical Research at the University of Tasmania, which is led by Professor Graham Zosky. And it was funded by the Medical Research Future Fund. And really the impact and novelty of that work lay in its sheer scale. It was worldwide the first and the largest forensic investigation of characteristics of the emissions generated from actively processing engineered stone and other types of stone with sufficient scale. And by sufficient scale, I mean 50 plus samples that allowed us to identify components of these materials that could be posing the greatest risk to health. So in a similar way to phase one of our research, we looked at the material science of the dust particles, but this time we looked at 50 resin-based engineered stones. Most of these were conventional, traditional, high silica engineered stones, but we also included some new generation novel reduced silica engineered stone products as well. Once again, we looked at natural stones for comparison, and we also included some non-resin based building materials, some of which are actually used as alternative products for benchtop making. And in terms of the lung cell response, so we exposed the dust to lung cells for 24 hours and measured the response. By lung cells, I mean, we looked at two types of cells, so human alveolar cells and lung macrophages. In terms of cellular processes, we focused on two different types of processes that relate to lung injury. One is cell death, so cytotoxicity and inflammation as well. We also undertook quite a few statistical associations to determine, firstly, whether there was any differences in lung cell response among the different stone types, and also to identify any associations between lung cell response and the different physical and chemical characteristics of the particles. So some results. So this graph is showing a particle size distribution of the different stone samples that we looked at. Each line on this graph represents a sample, a stone type that we included in our study. So the straight black lines are engineered stones, while the broken lines are natural stones. We can see this just confirms that more than 90% of the particles generated by cutting those stone types are under 1 micron in aerodynamic diameter. And we saw some variation among the different stone types as well. but I will just draw your attention to the first 3 samples where ultrafine particles were generated, and these referred to the reduced silica engineered stone products. Now, this is a small sample set, but given that these reduced silica engineered stone products, are being marketed as such safer alternatives, I thought it was quite an interesting observation to make, and certainly worth pursuing in the future. We used some new techniques, actually very similar techniques to what Professor Emily Sarver used to look at the morphology and elemental composition of ultrafine particles, which is quite novel because if you've worked with particles, you would know that ultrafine particles are inherently hard to capture. But we managed to get some, and we looked at them using scanning electron microscopy, and it just sort of confirmed that even in the ultrafine fraction, you get mostly crystalline silica particles, which is evidenced by those very sharp, jagged particles agglomerated together. And you might observe some bright spots on there as well, which relate to some metals. So even in the ultrafine fraction, you tend to see the similar composition, which is high levels of crystalline silica and some metals. We identified metals like copper, iron, titanium, and cobalt. And in terms of chemical composition, so this is a graph showing the total respirable crystalline silica and resin content of the different stone types that we looked at. So the blue bar represents quartz, the orange bar is cristobalite, and the gray bar is resin. So once again, there is a little bit of variability in the total RCS content of the dust particles. I should just mention that crystalline silica has different polymorphs, such as quartz, cristobalite, and tridymite, of which quartz and cristobalite are the most commonly occurring ones. And this is what we saw in our engineered stone dust samples as well. So the engineered stone products generate high levels of crystalline silica in the form of both quartz and cristobalite, which makes it important that we're looking for both polymorphs when we're doing silica monitoring in the workplace. The reduced silica engineered stone products, as per their manufacturer's claim, they indeed generated lower levels of respirable crystalline silica, again, as a combination of quartz and cristobalite. It was quite interesting to see the resin content of engineered stones in general were about 15 to 18% on average, with no major difference between the high silica engineered stones and the reduced silica versions of these products. The reduced silica engineered stone products indeed have sometimes similar levels of respirable crystalline silica as natural stones and some of the building materials. But the point of difference is natural stones do not contain resin. So once we understood the emissions characterization in breadth and in depth, we then started the lung cell response experiments. I should add that this part of the project was fully led by Professor Graham Soski, but I would include some highlights of the project here, which is firstly, quartz was significantly associated with the inflammatory response in lung macrophages. And this is really quite an important observation because there has been this consistent rhetoric that the crystalline silica content of engineered stones is a key driver of disease severity in this occupational group. However, the picture is not that simple because we also saw some strong association with macrophage toxicity from metals, in particular cobalt and aluminum in the dust. This is perhaps not surprising because, as I've shown before, the ultrafine fraction of these products also contained transition and heavy metals such as cobalt. So, this is more so to think about the implications in the workplace. My exposure science hat tells me that I've reported ultrafine particles with these elements, but is there any data available, not to my knowledge, about the efficacy of respiratory protective equipment that workers use against ultrafine particles? Because as we can see, we've got some association between heavy metals and macrophage toxicity. The observation or the rhetoric that crystalline silica might not be the only driver of disease pathogenesis is sort of supported by our next point, which is that even the reduced silica stone products also induced a strong inflammatory response. And again, this is quite interesting because, as you may know, there's a ban on high silica engineered stone products under consideration in Australian jurisdictions. Now, I know I might get the question, but what about the response between the high silica and the reduced silica stone products, which is a very good question, but I don't think we are at the point to really identify that yet, because even though this experiment was a large scale, the reduced silica products that we included, we only had 3, and there's a reason for that, because when we set up that experiment more than a year ago, these products had just started emerging, and we got 3 stone products to include in our study. But it's certainly something to include in future work. And finally, all these components that I discussed today didn't quite explain 100% of the variability in the macrophage cytotoxicity and inflammation that we observed in our experiment, which leads us to believe that there might be other contributing factors to disease pathogenesis. There might be some other surface characteristics that we didn't quite quantify in this experiment, or it could be, the VOCs generated at the same time. So that really brings me towards the end of my talk, which is what is next? Like I said, and there is a ban on the use of engineered stone products in Australia under consideration. And in light of this, there's been quite some development on the production of reduced silica or no silica engineered stone products, some resin-based, some not. And given the enormous harm that engineered stone has caused and is continuing to cause workers, I think it's absolutely imperative that we understand just how safe these products are. And this is a personal research direction for me. As Dr. Edwards mentioned, I've been awarded a fellowship to investigate exactly that. The work included in the fellowship will significantly build on some of the results that I've presented today, and also address some of the research gaps that we've identified in the last couple of years, including the contribution of VOCs to disease pathogenesis in this occupational group. Finally, I will finish by saying that we are well aware that silica dust is not limited to the manufacturing industry. It's a hazard in several other industries. And we have quite a few initiatives in the pipeline that relate to occupational lung disease prevention. For example, there's quite a bit of momentum at the moment on the use of real-time monitors for monitoring in the workplace. And we have a program of work set up to investigate the role that they might play alongside conventional sampling in dust-generating industries, particularly quarrying and construction. Ultimately, we aim to apply our exposure science learnings from the manufacturing industry and other with the aim of preventing disease in those industries. And I think that is it. Thank you very much.
So thank you, Chandnee. Questions? Who's coordinating online? Anyone from the audience? The microphone there.
Oh, thank you, Keith Adam. I noticed you recorded the levels of particularly of aluminium and cobalt, and I wondered whether you'd actually identified where they were from. Were they from the stone, or might they have been from the grinding wheels? And if so, it might have implications for other places where cement and things are cut as well.
Yeah, I've had this question before quite a few times actually, and that is a fair question. As far as I'm aware, it's given the variability among the different stones, and we've looked at scale now, and we tend to see similar levels. So I would say it's certainly from the stones themselves.
Any online questions? Thank you.
Yes, we have one from Alan Williams. It says you indicated that cobalt and aluminium were associated with macrophage toxicity. Are you aware of any mechanisms that would support these metals being a cause of macrophage toxicity? Or is the association simply because these metals are present alongside quartz in these products?
Very good question. Look, I would probably defer to Professor Gramsowski to answer these in details, but as far as I'm concerned, there is ample evidence in literature that metals like cobalt and aluminium, particularly cobalt, is highly toxic to the respiratory system. Also, when we undertake the statistical associations, we tend to separate those variables to understand, particularly for that reason, to understand the contribution of the factors.
Question at the back.
Thank you, Doctor. Good presentation. The question I have is, what's the percentage of silica that were measured during your tests from those bench tops? If you have.
Sorry, I can't really hear.
Sorry.
I couldn't really hear.
Can you repeat the question, please?
The question is, what's the percentage of silica that were measured during your tests of those samples of the size characterization that you've done?
The percentage of crystalline silica in the samples, so it depends on the type of sample that you're looking at. So like I showed before, so if you have a high silica engineered stone product, you're going to generate high levels of respirable crystalline silica, and it tends to follow that trend. So if you reduce the amount of silica in your bulk product, you're going to generate lower levels of respirable crystalline
During your
silica.
test, did you measure the % silica dust?
Yes. Yes.
Another online question.
Yeah, we have a question about whether you investigated the difference in percentages of ultrafine particles between the engineered stone, sort of traditional engineered stone, and the low silica engineered stone, and that compared to the natural stone.
We've done, we've certainly compared the ultrafine fraction between the different types of engineered stone products, and we have compared high crystalline silica content engineered stone products to natural stone products. So I will say yes. And there is, even looking at the graph of particle size distribution, those three products, at least the ones that we looked at, were consistently on the lower end of that, or that particle size distribution, so very ultrafine particles. So yes, a higher contribution of ultrafine fraction for the reduced silica content products.
What we've heard, here's another question. Good.
Oh, sorry. I was just wondering, with the VOCs that are identified in regards to engineered stone, is that a blanket? Are you finding VOCs in most of your engineered stone, or is it just a select few?
It was a select few. When we, yeah, I can send you the short communication paper. We looked at a few high crystalline silica resin-based engineered stone products, and they were pretty consistent. So styrene and phthalic anhydride are among the few VOCs that were detected, but we sort of focus on them too, because for their lung irritation potential.
There's another question at the microphone down the front, please. While we're waiting for the microphone, the observation I would make when you juxtaposition the presentation by Professor Sharma this morning, looking at the characteristics of the dust in the mining sector and the characteristics of the dust we're seeing in the engineered stone sector, what's the common theme? Yes, silica is important, but also the silicates and the other products that are in the respired hazard. That has seen the resurgence of the pneumoconiases in the mining sector in Queensland, as well as the pneumoconiases in the engineered stone sector. Question down the front.
Hey, Chandnee, thanks very much. Fantastic presentation. Really great work as well. Just wondering, with the finding of an increased percentage of ultrafine particulates, less than 0.5 of a micron and lower, what are the implications from an exposure science potential for engineering and solutions, but also what's the most appropriate respiratory protective equipment in those cases where you may not have sufficient pickup of very small particulates?
I think that was my question to probably occupational hygienists and other people in the audience as well, which is, I mean, there might be data available there, but none that I have seen, which is now that we have identified all these hazards, could we implement control measures to target it towards these particular hazards to mitigate exposures? And ultrafine particles is just one of those hazards that the workers may or may not be protected against while wearing RPE, assuming they are wearing RPE. So I think my answer is I'm not sure.
Excellent. So we'll move on now to our next speaker. The questions that might be online or in your audience will hold over now until the panel session. Our next speaker is our multimedia personality of the day, Kate Cole, and she's going to be presenting When the Dust Doesn't Settle, reflections from the National Silicosis Prevention Strategy Expert Steering Committee and the concerns for the future burden of silica-related disease across the various industry sectors. So Kate Cole is an OAM, is the immediate past president of the Australasian Institute of Occupational Hygienists and was the co-chair of the National Silicosis Prevention Strategy Expert Steering Committee. Her work on preventing silicosis has been informed by the completion of her Winston Churchill Fellowship and her extensive work on the major infrastructure projects in Australia and abroad. In recognition of her contribution to the workplace health and safety, Kate was awarded the OAM, the Order of Australia Medal, and was included in the 2022 Australia Day Honours. Kate works as an independent consultant while completing her PhD at the University of Sydney when she is researching respirable crystalline silica exposure in tunnel construction industry. Welcome, Kate.
Thank you so much for the opportunity to speak with you today about a topic so important as silicosis and my reflections about what's happening and some of my concerns for the future. As was said, I am an independent consultant, so I come with a disclaimer. I work for a lot of different people. I am not speaking on behalf of any of them. I was the co-chair of the National Silicosis Prevention Strategy Expert Steering Committee, but I'm not speaking on behalf of the Lung Foundation Australia or the Federal Department of Health and Aged Care. I am the immediate past president and the chair of the External Affairs Committee of the Australian Institute of Occupational Hygienists, but I'm not necessarily speaking on behalf of the AIOH. And I am a PhD candidate at the University of Sydney, and I will be talking about that today. So, recent estimates of 10,000 cases of lung cancer and 100,000 cases of silicosis from current exposures to respirable crystalline silica are alarming. There is a risk of me putting these numbers up. Maybe half of you will go, well, that's a really big number. It's great to quantify it. And half of you might go, oh, it's just a number. Because as it's been said many times, statistics are just numbers with the tears wiped away. So I want you to think about all the people that you know, your family, your friends, your work colleagues, those people that you forgot to defriend on Facebook, like everyone that you know. It's highly likely that that's less than 100,000 people. So put that into context. If we keep doing what we have always done, then things are not going to go very well for us as a country. So I had hoped to stand here today in front of you and celebrate the prohibition of the use of engineered stone, that decision that I had hoped would be made on Friday, but alas, no. The need to prohibit the use of stone or engineered stone in Australia has been the subject of much discussion since it was originally recommended in the National Dust Disease Task Force to curb the increasing numbers of silicosis. Oops, sorry, back. With one in four engineered stone workers with a silica-related disease in some Australian states, the engineered stone industry is a prime example of what happens when our work health and safety frameworks fail, and that our policies at the time were not sufficient to keep Australian workers safe. So reading the decision regulation impact statement on Friday afternoon, or in my case, 10 minutes before a live TV interview with the ABC, which was fun, or over the past few days, you may have read it, only further reinforced why a ban is needed. I think Dr. Ramkissoon was very modest in her bio, but I would just like to let you know that she led the expert review, the independent review that was commissioned by Safe Work Australia that informed this report, and it's something that we should all be very grateful for. So there were many clear and direct statements in the decision rears, and I'll be honest, they were really refreshing to read as an independent scientist. There was no media spin, there was just facts. Importers, suppliers and manufacturers of engineered stone products have failed to comply with their upstream duties to ensure that these products are without risks to health and safety of workers who will use these products. A very clear statement. There is also no evidence that lower silica engineered stone poses less risk to worker health and safety, despite what the engineered stone lobby may put out in a media release. And lastly, the cost to industry, while real and relevant, cannot outweigh the significant cost to Australian workers, their families, and the broader community that results from exposure to respirable crystalline silica from engineered stone. So best estimates are that engineered stone workers make up around 2%, at least that's what it said in this report, around 2% of all those who are exposed to silica dust at work in Australia. But they make up around 80% of all accepted workers' compensation claims in Australia. That's why it's so important. Because without a ban, we are really not taking occupational disease seriously in this country. We just pay lip service to it. But aside from the very real risks in workplaces to people who work with engineered stone, keeping this product in our workplaces actually impacts workers at risk of silica-related diseases in other industries. It has other unintended consequences. Because keeping engineered stone in our country means that our resources are focused there. It means that our jurisdictional regulators have to put resources and money there, funding there, people there. But this is only around 2% of those that are exposed to silica dust at work, as I said. So we absolutely need to ban the use of engineered stone in Australia, but the silicosis issue is actually much larger than this. And that's why the National Silicosis Prevention Strategy is so incredibly crucial. The National Silicosis Prevention Strategy and the National Action Plan were part of a number of recommendations from the National Dust Disease Task Force. And in terms of where it sits, it aims to address recommendation 3 from the National Dust Disease Task Force report, which is to prevent the risk of exposure. Its development drew on contemporary public health, work health and safety, disease prevention, respiratory health, safety knowledge and literature, and it was commissioned because of a more comprehensive view or effective prevention system for silicosis in Australia. So the development of the National Silicosis Prevention Strategy, which is a long word, so we call it the NSPS, and the National Action Plan, we call the NAP, was awarded to the Lung Foundation Australia. I co-chaired the expert steering committee alongside Dr. Ryan Hoy, who was the chair, and my area of, I guess, most focus was obviously on prevention because I am an occupational hygienist. There were 5 priority areas that went out for consultation in the NSPS or the NAP that you probably saw. And again, the one that I was most interested in was priority area 1, which is workplace risk reduction. So within that priority area, you probably already know that there was the need to prohibit the importation and use of engineered stone way back then. And Dr. Ramkissoon and Associate Professor Gaskin, their work has been fantastic at explaining why this is so incredibly important. But if I put the prohibition aside for a moment, I'd like to talk about some of the other activities that must be urgently progressed across at-risk industries to reduce the level of exposure to silica dust. So So we know from the modelling performed by Curtin University, and let's be honest, just being an occupational hygienist, that higher order interventions have the greatest effect on reducing future lung cancer and future silicosis cases. So the greatest impact is seen from reducing exposures to workers in the construction and in the mining sectors, given their large size and the level of exposure. And we'll put tunnelling in the mix in there as well. Things like dust suppression, wet cutting methods of all different types of product, including concrete and grinding, that type of product, for example. Unfortunately, there still is a very low level of knowledge, I would say, on the risk posed by dry cutting into concrete across our country. And while banning the uncontrolled dry cutting of engineered stone exists in our legislation as it should, it must be extended to all silica-containing materials if we are serious about eliminating silicosis. So what we already have in the Australian Capital Territory, for example, and in the Code of Practice for Queensland, for example. And while eliminating the source is always the best solution, hence the prohibition of engineered stone, focusing on minimising the amount of dust that's being generated into the air is absolutely the next best thing. Because once dust is in the air, as we probably all know, it's very, very hard to control. So I like to use this really basic diagram to explain that. So if you can imagine for a moment, I just take a strand of my hair and I hold it up. I make a little particle out of it. That width, it's around 100 micron. I have thin hair. It's around 1.5 meters up from the floor. Pretend there's no ventilation in this room and I let that particle go. It'll take seconds for it to drop. But that's not the size of respirable crystalline silica, which we know is around less than 10 microns. And you just heard from Dr. Ramkissoon about the particle sizes that are generated when we cut into engineered stone. So we know that they're quite small, less than 1 micron. But we also know that dust isn't generated in just one discrete particle size. It's in a range. So when you're cutting into anything that contains crystalline silica, you're generating particles that take minutes, that take hours, that take days, and take months to settle. And this is why focusing on the source, focusing on dust suppression, focusing on wet cutting methods, focusing on extraction of all cutting and grinding is really important. And I can appreciate that there's been, or there might be some pushback. There's been pushback at least in one jurisdiction, because I do understand that change is really hard. I get it. You know, cutting with water or using HEPA extraction is a little bit more expensive upfront, but I guarantee you it is cheaper in the long run. It's much cheaper than a case of silicosis. It's much cheaper than a worker dying who is a person just like you and me, dying from a completely preventable occupational lung disease. It is cheaper than the burden we're currently putting on Australia's public health system, which is already incredibly stretched. Now, we've had a reduced workplace exposure standard in this country for some time, and we've had news recently that this will be further lowered, as we all know. But what is a standard if it is just on a piece of paper and it's not complied with? In a peer-reviewed survey of occupational hygienist views in Australia that I led and published last year alongside my colleagues from the Australian Institute of Occupational Hygienists, great to see some here, there was a clear level of concern of the level of overexposure to silica across numerous industries. And in that study, one of the most effective regulatory prevention strategies suggested by survey participants was the mandatory reporting of exposure exceedances. So it's one thing to have laws on paper, it's another to achieve compliance. And this supports an important activity that's proposed in the National Action Plan, which was the need for mandatory reporting of silica overexposures or exceedances of the workplace exposure standard or the workplace exposure limit, whatever it shall be called, to jurisdictional regulators. And while regulators may receive notifications of disease, with silica, we're dealing with a long latency period and an incurable disease. And while there's transparency in some industries, like in mining, you get this data, and Peter Knott shared some amazing data. Can you imagine having that type of data in a non-mining industry like construction or tunnelling? It just doesn't exist. Exposure data collected in tunnelling, building, demolition, that's held by the employer. It's not published anywhere. It doesn't go anywhere. The only way a regulator knows that he has a problem or they have a problem is if there's a disease notification, which of course then it's too late. So I've just shared a few items with you that are proposed in the National Action Plan that I believe are crucially important, but there are obviously many, many more. But they're all a crucial part of eliminating silicosis, or at least reducing the burden of disease that we currently are on a trajectory to receive in Australia. The National Action Plan is currently being considered by government, and I'm very proud of the work put into that plan by many stakeholders to get it where it is today, and we imminently await its release soon. So the first diagnosed case of silicosis from engineered stone in Australia, I believe, was reported in around 2015. And 3 years later, thanks to increased screening, the cases just really started to climb. There is a huge focus on engineered stone, and this is entirely appropriate. But once engineered stone is banned, just humour me because we will ban it. So once it's banned, where is the next place that we need to look? I would like to share some insight into my own perspective of where I think the next largest cohort of cases may come from in Australia, and that is tunnel construction. I am many things, and one of them is a PhD student at the University of Sydney undertaking research into this very area under the supervision of Professor Tim Driscoll and Dr. Heidi Gilchrist. And there's been a few alarm bells recently that I'd like to share with you. In 2021, a paper published in Queensland actually reported 8 tunnellers with chronic silicosis. They had 10 years minimum dust exposure, diagnosed during pre-employment medicals. Their average age was less than 50. They'd all worked on large infrastructure projects across Victoria and New South Wales before they travelled to Queensland to commence work on a project. Last year, a case of severe silicosis in a tunneller was reported. Again, he was under 50 and he had worked across many tunnelling projects, and eventually he was picked up through workplace surveillance. And when asked the question in New South Wales Parliament last year, SafeWork New South Wales shared information that 21 workers were diagnosed with silicosis from tunnelling work in New South Wales in the preceding 5 years. There's been a significant amount of tunnel construction in New South Wales, my home state, in the past 5 years, so this is incredibly concerning. But I'm sure most of you are familiar with mining, and I'd just like to dispel the myth that tunnelling and mining are similar. They are two completely different beasts. The vast majority of tunnelling, or 98% of all the tunnels that have been built in the past 4 decades, have been in built up, very urban areas or cities. These projects have access to the very best technology and systems available because of their location and their ability to draw resources in. But their project life is really short, so maybe only a couple or a few years long each project. So where investment in technology and equipment can be maybe amortized over the life of a mine lease in 50 or 100 years or something like that, these projects have to draw down the cost in just a few years only. There have been 68 tunnel projects that have either been constructed or are being constructed in the past 40 years, or the current working lifetime of many tunnellers. And if a tunneller has silicosis, it is from one or more of these 68 projects. So I spend a lot of time understanding what these projects are or were like. As you can see, the vast majority are in my home state of New South Wales and Sydney specifically, and that is the area with the highest silica content in our rock. It is sandstone and it is around 75 to 90% quartz. So the challenge with tunnelling is, although it might seem like an issue at an individual level, it's actually bigger than that because we're always tunnelling. This time bar chart shows the number of tunnels being constructed at any one time across each state in Australia. It is a highly specialised activity, and so it's supported by a highly specialised workforce who travels and moves to each one of these tunnelling projects. So to understand the true extent of exposure to silica or the burden of disease, you have to look at the conditions that apply across the industry, not just on one particular tunnel. You know, around 60% of all the tunnels that we build are for the purposes of transportation, And around 35% or so are for energy, water, and telecommunication, with the rest being other utilities. And I will say there are some really great tunnelling projects that absolutely put the health and safety of the workforce ahead of everything else and do some really, really wonderful things. But equally, there is the opposite end of the scale. And unfortunately, workers travel to all different projects, so they're subject to very changing workplace conditions. So we know that tunnelling in the past was not always done in a way that was protective of workers' health. On the left, you see Sydney Harbour's second crossing. That was a photograph that someone thought was a good idea to publish in Australian Geographic. It shows two gentlemen standing on top of a roadheader without a cabin. When you zoom in, cannot see any respiratory protection, and you see the dust and that sandstone at around 75% crystalline silica and a fairly ineffective ventilation system. On the right, you see a very similar photo. That's from Queensland's Airport Link. That photograph, it came from the coal workers' pneumoconiosis inquiry. It was tabled there, along with a whole bunch of other silica data showing just how high those exposures were during the development of that project. Now, we wouldn't dream of building tunnels like this anymore, or would we? Well, there are many questions, and on the screen are just some of those questions that I hope to answer as part of my research. The very first one that I'm currently attempting to answer is what is known about the type and prevalence of work-related diseases amongst tunnel construction workers. Absolutely, silica-related diseases are very prevalent. You name the types of diseases that are caused by silica dust exposure, they seem to all feature in one way or another in a tunnel construction worker. But tunnelling also uses many other hazardous chemicals, so predictably, there are other illnesses and diseases that are reported internationally from those types of exposures. I also aim to understand what is known about silica exposures to tunnel construction workers at an industry level rather than an individual project level. And I would like to understand the structural enablers and barriers for silica-related diseases in this really important cohort. And lastly, and most importantly, to try to figure out and to support our country on what policy aspects have had the greatest impact on disease prevention in tunnelling. Because when the dust settles, the day after, we ban the importation of use of engineered stone in this country, which we absolutely have to do, then that is the day that we must focus our attention to this next important sector. Thank you.
Questions from we've got the microphone down the front, please.
Thanks so much, Kate. Dan Chambers. My question is about, I always struggle with workplace exposure standards, which have been developed, as far as I'm aware, always in the primary prevention setting. So what do you do with people who are already diseased? And as far as I'm aware, there's no data about what a safe limit is. Of course, the obvious thing to do is say you can never work in that industry again, but sometimes that's not necessarily practical. So appreciate your thoughts.
Yeah, that's a really good question. And I think that's where the partnership between occupational hygienists and occupational physicians really does kick in, and doing those workplace assessments to find safe alternatives for those workers to continue to work where that is possible. Obviously, there's a range of silica-related diseases, early stage silicosis and very late stage silicosis. And depending on where a particular person is on that spectrum or on that journey will again, also depend on what options are available to them. I think the saddest thing that I have seen is tunnel workers who have worked in tunnelling for 10, 15 years, have been diagnosed with progressive massive fibrosis and can no longer work in that industry sector. And that is their family, that is their community, that is absolutely everything. And so to watch them have to leave that industry is incredibly, incredibly heartbreaking, which just speaks to the importance of prevention to start with.
Any questions from the online audience?
There are, but they're sort of being answered by other people online, which is entertaining. So Kate, there was a question around whether we know any information about cases in Brisbane that might have been related to the Brisbane Airport Link Tunnel project.
Yeah, so this is some information that I hope to be able to independently research. So I don't have that information for you. I will say that as an independent consultant, like many occupational hygienists, I work as an expert witness, and there are projects that are routinely featured in silicosis cases of tunnel workers, and that is absolutely one of them, yes. So, and that is not surprising when you look at the data that was shared in the coal workers pneumoconiosis inquiry and the high levels of silica dust that were reported on that project, or indeed the photographs that were shared, and I showed one of them with you today. So that level of dust, you think about a worker being exposed to that level of dust for 12 hours a day for a year, it racks up pretty quickly. So yes, I don't have anything else other than that.
Is there any data on the roles that these workers that have been diagnosed from tunnelling were doing? Are they engineers or labourers, or is there any data on that?
I only have my personal experience, and I will say that it is very wide ranging. So as an occupational hygienist, like the many occupational hygienists that work in tunnelling, and can I just say thank you to every single hygienist that works in this sector. Your work is incredibly valued, even though I know it's hard. We still measure exposures to crystalline silica way back from the tunnelling phase, so in other support work environments. So just because it's not underground doesn't necessarily mean that it's not a risk. So there is a wide variety of occupations that all support tunnelling, and it's incumbent to have a really good occupational hygienist to go out to do those types of health risk assessments to really understand where those exposures occur, such that we can have really good controls in place to keep them safe.
Thanks, Kate.
I think another question from the audience.
G'day, Kate. Dean Barr here from RSHQ. Thanks for your presentation. I'm just interested in your thoughts from your role at the national level around what you think might need to change to our collective approach to managing health risks, given that we seem to be on the back foot, whether it's black lung in mining, stone bench tops, tunnelling. We're in this sort of reactive phase. What do you think needs to change to stop these from happening in the first place?
It's a really good question. I think that there needs to be some improved regulations or systems around product stewardship and importation of materials into Australia, and some more questions asked about new materials that are coming in, and that mainly relates to manufacturing and stone. But when it comes to preventing disease and being on the front foot, you know, occupational hygienists measure airborne exposure to a myriad of things, but that data isn't always acted on. So sometimes we know that there is a problem, but we can't say anything, or a particular employer doesn't take action. Having a requirement for mandatory reporting of exceedances of the exposure standard makes that easier. So a regulator now will have that information, and it's a fantastic leading indicator before a disease develops. So that's what I hope is carried in the National Action Plan.
Dean, that's a question subject to my heart. And as the chair of the session, I can take a privileged position of commenting from the stage. There is a fundamental failure of our regulatory framework. When we ask people to do a risk assessment, health and the latent diseases are not in the forefront of consciousness of people making those decisions. So when the risk assessment is in the hands of the PCBU or the SSE, and they're not informed by the medical issues, the knowledge that we have as occupational physicians around the latent diseases, the system is fundamentally failing Australia's workforce. It's much better in the mining industry in Queensland because we do have a network of historic NMAs and now AMAs who do have an insight and can inform the decision-making of the regulator in Queensland. That does not occur elsewhere. It is a failing of the model laws. It's the fragmentation between mining sector and the other non-mining sectors, building and construction. So until we actually have the fundamental change in our regulatory framework that takes into consideration the health consequences of latent diseases, from the cancers to the silicosis, the pneumoconiosis, the the chronic obstructive airways diseases, we will not have effective protections for the Australian workforce. Herein endeth the lesson. I would like to introduce now our next speaker. We can further the discussion of these subject matters in the panel session later. So the privilege of rank. Thank you. So our next speaker is Professor Dan Chambers. Dan is a thoracic transplant physician, Professor of Respiratory Medicine and the Executive Director of Research at Metro North Health, Australia's largest health service. Dan has graduated from the University of Queensland with the University Medal. He trained in Australia and the UK, and he is widely acknowledged as a clinical expert on advanced lung disease and transplantation. His research and clinical trial program is one of the world's largest, investigating novel drugs, cell and other treatments for people with lung fibrosis, silicosis and transplant rejection. He has been named one of Australia's foremost researchers in all fields and the top researcher in the field of transplantation for each of the past 3 years. He is deputy editor of the world's premier transplant journal and the only Australian to have directed the International Heart and Lung Transplant Registry, the main source of evidence for the practice of cardiothoracic transplantation globally. He's personally cared for over 100 young Queenslanders with silicosis. Today, we've asked him to talk about the diagnosis and management of silicosis, the current status and future trends. Please welcome Professor Dan Chambers.
Thanks so much for the introduction, Graham, and thank you, Nikki, for the opportunity to speak. And amazing for me as a respiratory physician to learn some geology and actually to see the expertise in the room. If I'd been asked to give this talk, say 5 or 6 years ago, it would have been very short because there was no treatment for silicosis and there still are very few treatments available. And we actually knew not much about the diagnosis. So I'm actually going to introduce you. So Kate, I think, mentioned about the 100,000 Australians who probably have or will get silicosis. I'm going to introduce you to some of them. 100 is actually an underestimate. So I've seen hundreds of young Queenslanders actually from and interstate with this disease. Some of them have died, some of them are near death, and a terrible problem. So this is Craig, and he's one of my patients, and he's got progressive massive fibrosis, and certainly affected his health. But as pointed out, it's really wrecked his family life because he was not able to work, and caused a whole stack of problems beyond there. This is Adam, who is the sole carer for 6 children, including one with a disability. He's their main provider. So what was he going to do when he received a diagnosis of PMF? Leave his work and not be able to provide for his children. So, really, really difficult situations. I had hardly ever seen someone with silicosis in Australia until about 2018. It was the first time I saw someone from the Gold Coast, and it was actually a colleague on the Gold Coast, I think affiliated with Graham, who first called me and said, it's incredible. I've seen in the last 2 weeks, I've seen 7 people with progressive massive fibrosis. So it was immediately obvious we had a massive problem on our hands, and it was immediately obvious that this is going to be a team effort to stamp out this problem. So I knew that our role in the transplant program and the advanced lung disease program was to identify better ways of diagnosing people quicker and to consider whether we could offer treatments that might prevent someone requiring a lung transplant, which is not a great option. And I'm really, although this is a team effort, there's a huge amount of things that need to be done here. I'm going to focus on these last 2, of course. So just a little bit of radiology, if you'll give me the opportunity. So this is silicosis, all right? So this is a CT scan, and we're looking from this person's feet. So the arrows point to their right lung on the side there. And this is the typical early finding in someone with silicosis. So it always affects the top of the right lung first, and the lymph nodes. So the red arrows point to lymph nodes in the middle of the chest. And then eventually there's worsening reticulation, and some scarring develops. And then the final slide there is progressive massive fibrosis, where there's this conglomerates of fibrosis, respiratory failure, and ultimately death. In contrast, this looks pretty similar, right? But this is actually someone with sarcoidosis, which is a different, there's a relationship between the two, but a different disease. And so one of the questions, sometimes it's often very obvious what the diagnosis is, but not always. So one of the things we set out to do early on was to see if we could develop ways to assist in making a diagnosis, which is very important, not just for treatment, but also, for a whole lot of other reasons, like, workplace activity, compensation, et cetera, et cetera. This is another disease that actually looks fairly similar. So you might be able to see some fluffy grey dots amongst the lungs there. So this is actually a condition called respiratory bronchiolitis interstitial lung disease, which is related to smoking. This is not silicosis, but it looks quite similar. And so this is where some of the confusion has come, and that's why we set about developing a test for silicosis. So actually the first person I rang when my colleague in the Gold Coast called me was my chief scientist in my laboratory at Prince Charles Hospital, explained the problem. So we do a number of things in the transplant program that are very standard. One of them being this procedure called a bronchoalveolar lavage, which is where we go down with a camera, place it into the lung, wash in some salty water and suck it back out again is basically what we do. And so it's a really great way of very easily, very, very safe accessing the alveolar space in the lung. And we obtained the fluid on the left there is typically sort of grey sort of fluid that comes out, which is full of macrophages. And this is what we see just under light microscopy. So we see, so the cells should look like those little blue dots. So that's DAPI staining the nucleus, but these huge macrophages, way too big and stuffed full of this fluorescent green material, which is all oxidized protein. So the macrophages sit in the lung and their job is to chew up dusts and bacteria and other things. And that's exactly what they do when someone inhales silica. So we never, ever see, pretty much never see free silica particles in our patients. It's always inside the macrophages and they get stuffed with this stuff, can't digest it, accumulates, and that triggers the fibrotic response, as we heard really nicely from Chandnee. We've also done, so we've done a lot of work on what this looks like in workers. So this is actually a sample from a Queenslander with engineered stone related silicosis. So this is a BAL sample. And this is scanning electron microscopy. And actually it was remarkable. I hadn't seen Chandnee's slides before, but remarkably similar to what she showed from her, her derived stone. This is actually what's in someone's lungs. This is like a crime scene. And you can see with SEM there, silica in blue, oxygen in yellow, green, it's almost all silicon dioxide, but there are some metal contaminants in there as well. So in this case, a little bit of red, a little bit of aluminium. And because the engineered stone products are made to look beautiful for your kitchen benchtop, the other things we've seen a whole range of stuff, including this is some glass. So this is actually about 50 microns. So I have no idea how this managed to become lodged in someone's lung, but this has come out of one of our workers. So some glass there and other things, bits of shell and so on, all of these materials. So what we did was we did a pretty simple thing. So we just devised a test where we count the number of crystals that are sitting inside the macrophages, inside the BAL fluid, and then correct that for the cell number. And so we developed what's called we call it a crystal burden. We know it's 99% of it's silicon dioxide, but we call it crystal burden. We've published on this, and this is highly accurate to work out whether what we're seeing in a lung is in someone's lung is actually silica, or is it sarcoid or rabi-ILD. And so you can see in the middle there that the workers who have silicosis usually about a log higher crystal burden, as you might imagine. This is another patient of mine. He's awaiting transplant at the moment. This is Frank. So he actually does not have silicosis, but his disease is also related to silica exposure, as he was a stonemason. So he developed scleroderma as a result of silica exposure. A very old association, Erasmus syndrome it's called, and then he's developed a progressive fibrosing lung disease and is in respiratory failure, and he's currently waiting transplantation in Queensland as a result of the scleroderma. But the fundamental problem was still his stonemasonry. The other thing we knew from, so this is the Spanish cohort that many of you have probably seen, but so some great work in Spain that so this is 106 stonemasons in Spain, engineered stone exposed, very similar to our cohorts here. We knew that from this cohort that even if you remove them from the exposure, 2/3 of these young men still had progressive lung disease after they'd been removed from the exposure. So although of course that's critical to remove them from the exposure, it's not enough to save a life. We also knew from some of the work we'd done early on that so this is just a graphic of what happens. So you inhale these particles, they're phagocytosed by macrophages. We know a lot about those macrophages now through some other technology that we've got, so we can work out how they become profibrotic. And we knew that that's what happens. And so we knew that if you could possibly remove these cells and their crystal load, then in the same way that there's a principle in medicine that if you've got a foreign body somewhere, you should try and remove it if you can do that safely. So you certainly don't leave a piece of metal in someone's eye, for example, because otherwise this is what will happen. So it's the same principle that we took. So there's a procedure that we do and most of the transplant centres around the world do and have done for decades for a different lung condition called a whole lung lavage. We've been doing that for a very long time for a condition called alveolar proteinosis, which essentially involves putting the person to sleep, intubating them, tube down each side, isolating the lungs with balloons, and then so we can ventilate one lung while we wash out the other lung. So this is a very standard procedure that the transplant programs all over the world do quite frequently for this other lung condition. And based on what we'd seen in the BAL fluid, and which is like a mini version of this procedure, we thought it was likely that this would help. So we got support from Queensland Health to undertake this procedure. And this is one of the whole lung lavage procedures ongoing. So that so the patients will obviously sleep and ventilated, and ventilating one lung while we pour in fluid in the uppermost lung, and wearing a vibrating vest, which really helps disseminate the fluid around the lung. We have direct vision at the bifurcation of the right and left main bronchi so that we can make sure that this person is ventilated on one side while we wash out the other side. Obviously not good if we're washing out both sides at the same time. And then literally rinse and repeat. And so this is fluid going in and out there in that shot. This is what it looks like when it comes out. So, it's usually about 25 litres of fluid that comes out, starts out very dark brown, sort of Brisbane river water, and then ends up kind of Sydney Harbour by the end of it. We do remove a huge volume of not just crystals, but very importantly, it's the pathogenic cells, it's the alveolar macrophages. And from some work that we've done with others, we know that those cells are then replenished from the bloodstream. So we remove the pathogenic cells, the macrophages are replaced by healthy cells from the bloodstream. It's a very straightforward procedure. The question is, does this actually help? And so this is another gentleman, if I could introduce you. Unfortunately, he's passed away. This gentleman passed away a few years ago and unfortunately could not make it to transplantation in Queensland. This is another patient of mine, Justin, who's still listed for transplant, and you can appreciate there, so he's got progressive massive fibrosis. So this is his plain X-ray. And even if you know nothing about X-rays, you can see the black bits of the lungs. You can just see that those have shrunk over time, and that's exactly what happens. It also unfortunately makes it much more technically difficult to do a transplant operation because the trachea is retracted into upwards into the neck, which makes it technically very difficult. The other thing we did, apart from offering whole lung lavage, and I'll go through a little bit of the information that we have about its efficacy. So usually what happens in medicine is when you remove something from someone, you throw it away. So instead of doing that, we've got a program, a biobanking program at our hospital, which with our patients' consent allows us to retain that fluid. And we've learned a lot from studying that fluid. And without going into any detail here, we have been able to discern exactly why these cells are profibrotic. And we've then we've been able to mine that information in silico, predict which drugs are going to target the pathways that we know are aberrant. And then we've constructed a phenotypic drug screen so we can actually screen candidate compounds with the primary cells from the humans who actually have the disease, which then means it's much more likely that the drug is going to be effective. And we've got some great information from that. One of the really interesting things we did, we had apologies to UQ, but We actually had a great collaboration, we have a great collaboration with Griffith Nature Bank. So this is Rowan from Nature Bank. It's an amazing facility. Lots of compounds from all over Queensland largely, so rainforest, reef, etc. Natural compounds, and we were able to screen a whole stack of compounds from Nature Bank, and we found one compound we can't actually turn into a drug, but it's from a rainforest tree in North Queensland. It's called endiandrin, which has potent activity to switch off the fibrosis in those macrophage cells. So coming back to, I've talked about diagnosis, talked about some management. There's still plenty of work to do there to prevent people from becoming really ill. The other thing that we're really interested in is, I've certainly seen, I've seen hundreds of workers, and I've seen many who, in fact, one really sticks in my mind. So a gentleman named Bob, who was in his early 40s, and he actually was pretty well. So he had very mild silicosis very early. But his main concern was that he'd introduced his brother to the industry, and his brother has progressive massive fibrosis, and they'd worked together, very closely for pretty much the same time, pretty much the same exposure. And I've seen this, I'm sure Graham has as well, many times. The same exposure, pretty much same factory, same exposure, same length of time. Someone's really ill and the other person's fine. So there's obviously a genetic component to risk. Of course, it's caused by inhaling dust, but there clearly must be a personal risk factor. So what we've done is done a little bit of genotyping. So there's a very well-known, no technical detail here, but it's a very well-known genetic risk factor for lung fibrosis. It's called MUC5B is the gene, and it's a SNP in the MUC5B gene. Normally 11% have the T allele in the healthy population. In pulmonary fibrosis, the other forms of pulmonary fibrosis, it's about 26%, something like that. It's a very strong risk factor. So we thought, oh, well, we'll probably find the same thing in silicosis. We'll find that there's an elevated number of patients with this SNP. In fact, we found exactly the opposite. So we found that this SNP is actually protective for silicosis. And we think that actually makes sense. We didn't predict that, I confess, but this gene actually makes mucin. And the T allele the G allele means you make more mucin, mucus. So this is probably protective because these people make more mucus and prevent the dust actually making its way all the way to the alveolar space. So there are clearly really strong genetic risk factors, and this kind of information, you could use this in a lot of ways, one of which might be, for example, to target health monitoring to those most at risk. We also know that if you develop medications that target a gene defect, they're far more likely to be effective. And we know there are other really strong genetic risk factors that we know from other forms of lung fibrosis, I think, which are highly likely to be causative of PMF in this disease. We haven't managed to be able to study those yet. And just finally, before I finish, the other thing I think that we could certainly do better on, and again, staying in my lane of, management diagnosis, is, it really strikes me that in Australia, we're a developed economy. We have amazing health technology. We have an opportunity actually to think positively about this and think, how could we help solve this problem, not just for our population, but actually for people all over the world, and particularly people in developing countries. So, it certainly strikes me that it is crazy that we are still using technology that's about 125 years old, largely, to do our health monitoring for our at-risk workers. So we're using spirometry and we're using plain chest x-rays, which are both about 120 years old. We certainly can do better. And I think there are plenty of opportunities there to be able to develop far better tools that are less invasive. So, CT scan in particular involves a significant amount of radiation, but actually far more sensitive and specific than our current tools. So we can really accurately predict who's actually at risk of developing worsening disease and who is not. So, for example, one thing we're exploring is the use of detecting really tiny particulates, sort of femtomolar concentrations of protein, which then, using amazing technologies that's actually only emerged in the last year or two, you can identify those proteins. And so we think we'll be able to link the information that we have from the lung washouts and all what we know goes wrong in someone's lung to develop better health monitoring tools, for example. And there are others who are looking at volatile organic compounds in exhaled breath as a possibility to undertake health monitoring. So I just wanted to introduce you just finally to my lab team and study coordinators at Prince Charles Hospital. So we largely work in the lung transplant field and lung fibrosis, but have managed to be able to divert some of our resources to try to help with this problem. So once again, thanks very much, Graham, and thanks very much, Nikki, for inviting me.
Right, open the floor to questions. We have one.
Thank you very much for the presentation. It was actually quite fascinating to see the technique of lung lavage that you were covering off. I think you actually touched on it briefly in the presentation. I might have missed it. When you actually do the lung lavage, what effect does that have on the disease progression? Does it slow it down? Does it actually, what effect does it have ultimately?
Yeah. So look, great question. So like many things in medicine, seems like a great idea. We should try and remove this stuff if we can do it safely. But does it actually improve long-term outcome? So what we do know is that it certainly improves in the right person. So it does not help someone who's already got established fibrosis, so PMF, for example. And the reason for that is very simple, that the silica dust and those cells are already encased in fibrosis in the lung. There's no way you can remove that unless you undertake a lung transplant. But those workers who have earlier disease where the alveolar space is stuffed full of those macrophages, full of crystal, full of oxidized protein, we can remove all of that. And we see quite dramatic changes in the CT scan in those workers, so improved immediate changes in the CT scan. What we don't know yet whether that translates into a better long-term outcome. So we've got an ongoing study in collaboration, mainly with Ryan Hoy and colleagues in Victoria, where we're following our cohort of workers who've undergone whole lung lavage, and we'll be able to compare those to a cohort of workers who have not undergone whole lung lavage in Australia and in Spain, so that we'll be able to compare outcomes. But of course, this takes years. We only started doing this about 3 years ago. Another question.
Hi, I have 2 questions. So firstly, when you were saying there's a way to look at the proteins for detection, which may be a future option, is that like a sputum or is that?
No, so there's a technology which allows, so it's an exhale breath maneuver, but it creates oscillation in the bronchioles and the alveolar space, so that particulates are exhaled from the alveolar space. And so you get tiny little particulates that are full of protein. So they have surfactant protein, for example, in them, which only comes from the alveolar space. So we know it's a technique that was developed in Sweden, and it's been used to investigate a number of different lung conditions, never in pneumoconiosis. And combine that, so that you get tiny little amounts, tiny amounts of protein, really femtomolar sort of concentrations. But there's also some technology using aptamers, which is a DNA RNA structure, to then detect tiny amounts of protein and identify them. So that technology's only been available about 2 or 3 years. So we think combining those two, is likely to be quite feasible. And we know the proteins that are abnormal in the lung fluid and macrophages.
Okay, so sorry, that's made it 3 questions now. Who will be able to perform that testing? Is it something that's going to be easily accessible for workers when it does get to that point?
That's what we hope. Yeah, I mean, there's a huge amount of work to be done, to demonstrate feasibility. But importantly, the machine is portable. So this is something that part of the issue is that you need to be able to deploy this to where people are who are doing this work. Otherwise, it's just not practical. So I know there are buses and trucks going around with CT scanners and spirometry and lung function. It's great, but could we do even better than that? And I think we can in Australia. We've got all of this technology. I think this is a solvable problem. It just needs resources put towards it.
Thank you. And thirdly, with the lavage, does that come into our clinical pathways at all? As when someone does get early detection, can it be included into the clinical pathways guidelines?
Yeah, I mean, there is no clinical pathway guideline for how you manage silicosis, but And to get to a guideline sort of level of evidence, we will need that long-term outcome data to demonstrate that this is really of benefit. You know, there's a point where, so, you know, it's always a matter of balancing risk and benefit. So we know this procedure, it sounds really complicated, but it's very simple for us to do this. It's very safe in our hands because we've been doing it for a very long time. So we know it's a really safe procedure. So therefore, even if it confers a little bit of benefit, that's great. We think it'll actually be quite beneficial in the right person. And probably the main thing will be making sure that it's targeted at the right person. So early, before someone has scarring, not so early that simply removing from the exposure is actually all you need to do. But that group in the middle where that's not going to be enough, we need to also do something else to stop them developing fibrosis, which then becomes self-perpetuating, and there's no answer to that. You don't want to get in that situation. And both Ryan and I have got patients where we look back and think, I wish we'd gone ahead and done the lung lavage 3 years ago, but it was very early back then.
And then fourth question, how do we get our patients referred to you?
Yeah, look, I'm very happy to see anybody. And we do use the BAL test also to work out who might benefit from a lavage, because we don't see a whole lot of crystal when we do that very simple test. Very unlikely that the lavage, because this is just a tiny version of the big thing. So we use that test to work out who's likely to benefit, along with a whole lot of other factors as well.
So the current clinical pathway guidelines gets you to the front door. So the supervising doctor will then trigger that process if we've got to the that front door to suggest that this may be the diagnosis in this particular worker. Online questions?
Yeah, we have a couple. The first question from Alan Williams says, Professor Dan, in your opinion, is there a threshold for severity of silicosis below which it's acceptable for workers to continue in the work that caused their disease, with additional controls, of course? Is there a standardized approach to deciding who can and who cannot continue in that type of work?
Well, that's exactly why I deflected that question to Kate, because I really struggle with that, because, and it isn't, I think it is always a matter of balancing up what is best for this person and completely removing them from, you know, the work that they are really skilled to do, they get paid well to do, and it's their social network, you know, may not necessarily be exactly the right thing to do in every circumstance. I think Kate's right. Try and redeploy someone to a place where, you know, they're much safer, but can still use their skills. You know, I think there has to be some compromise. Ideally, you just stop them being exposed completely, and you know, and generally my experience has been that younger men, almost all of them are men, will say, forget it. If I'm going to keep working in this industry, I've got another 40 years. I'm not going to do that. Yep. And so, you know, one of my patients has become a hairdresser, for example. But someone who's 5 years away from retirement, you know, there's a whole lot of factors to take into account. But that's exactly why I deflected that question to Kate. And, you know, we don't know what the safe limit of exposure is in someone who's already got disease. So it's a difficult question.
Thanks, Dan. There's another question here about whether there's any scope for stem cell research to attempt to regrow the damaged parts of a patient's lung.
So stem cell research, no. But having said that, you know, I think there are some really exciting treatment options that will be coming, because we now understand exactly why cells deteriorate in the lung. And so actually I was at a conference this morning with a colleague. So we've got some treatments that will regenerate, we think, but that's probably 2 or 3 years away before we go into humans and different disease.
There's one other question online. Do you think it would be an advantage to have TLCO as part of the standard screening of silica workers?
Yeah, so DLCO is the diffusing capacity for the lung. Look, I do think that is helpful. So it's an additional breathing test. It's very simple, you know, done as part of spirometry, but it does provide additional information about gas exchange in the lung. So it tells you something, it gives you information that you don't get from just spirometry. That said, I think all of those tools are pretty crude. You know, I think we could do a lot better, but, you know, they're the best we've got at the moment.
Professor Dan, that's
another question in the room.
Thank you. Just talking about DLCO, I think there's a paper that's only just been published by Ryan Hoy, which showed that it actually, as a screening tool, isn't a very good discriminator. It may be a very useful clinical tool, but at the low levels that you're likely to find in this, it was no more or less effective than spirometry, and even that's not all that effective.
Yeah, I don't want to defend diffusing capacity. I think it is a pretty poor tool, but so is spirometry. Yeah, and so is an ILO chest X-ray, really. You know, so I think we just, all of those tools, mate, they've got a place, but you know, I think we could do so much better.
Another question? Just for the rest of the audience on that, the current clinical pathway guidelines, which have just come into version 2, does have capacity to include tools like DLCO in that workup of the individual. So it's stratified, it's more complicated than the original clinical pathway guideline, but it's better targeted to be able to work up when these tests might add value. Question?
Thanks, Dan. Matt Brand, occupational physician. Great presentation and love your work. There are different recommendations and guidelines and legislative requirements for radiological screening for silicosis in Australia. Western Australia, for example, it's LDCT now. Queensland, I think we follow the Safe Work Australia guidelines, and it's ILO chest X-ray every 5 years, perhaps more often. There's heavier exposure. Might want to consider HRCT. Where do you think we're heading? We're obviously thinking about the higher radiation dose risk in LDCT compared to ILO chest X-ray, balancing that with the much higher sensitivity. Where do you think Australia is heading in terms of perhaps a more harmonious approach to the use of LDCT?
Yeah, look, I think the really important thing there is to realise that although it's a low dose CT, there's actually still significant radiation. It's not a no risk test. And, you know, it's pretty expensive as well. So I think it's going to be, personally, this is getting a bit out of my lane in terms of, you know, health monitoring, but welcome Kate's views. But, you know, I think it's going to be much more about, you know, stratifying risk and applying what tools we have available at the time to achieve the most effective health monitoring that we can, to pick up those workers who are truly at risk of developing disease in the future. And, you know, as I said, I think we'll have better tools than those tools, but of course, to generate the kind of evidence that we need for them to, you know, those kind of tools to come into policy, you know, it's, wow, at least probably not in my working lifetime, but we need to start.
One last question before we move to the next speaker. Any other questions? Can we wait for the panel?
Okay, thank you. Peter Aspinall, occupational hygienist also. Just in regards, you mentioned this may be a little bit outside of your lane, but you mentioned the scleroderma as a indication, and I was just curious whether you'd seen any link between the genetics and the scleroderma and maybe rheumatoid arthritis and those sorts of indications.
Yeah, so great question. I think that's a really fascinating question. So why does silica exposure cause an autoimmune disease or a number of autoimmune diseases? Look, I think absolutely genetics are going to come into play. And one of the other main genetic defects that we see in other forms of lung fibrosis causes a problem with the telomeric region in the chromosome, the end of the chromosomes. That's strongly associated with autoimmune disease as well. So I think it's pretty likely that if we look, and you know, we just haven't looked yet, we haven't had the money, we would find that it's a dysfunction in the telomere region, which increases the risk of PMF, but probably also those autoimmune conditions.
Thanks, Dan. He'll join us again after the panel session. Our lucky last speaker for today before the panel session is Nikky LaBranche. So Nikky is a research fellow here at the Minerals Industry Safety and Health Centre within the Sustainable Minerals Institute at the University of Queensland. She is pursuing her PhD characterising the impact of dust on the respiratory health of coal mine workers. So for which she has been awarded the AusIMI Education Endowment Fund Postgraduate Scholarship. So Nikky is a mining engineer with 15 years experience in surface and underground coal through her work in the US, Colombia and Australia. She's currently serving on the board of directors of the AusIMI
Awesome.
AusIMI
Yeah.
acronyms. Health and Safety Society and has received the John T. Boyd Young Engineers Award. So she's presenting characterisation of airborne particulates in Australian mines. Thank you, Nikki.
Hello there. Yes, lucky last today, but I had the pleasure of setting the agenda today. So really wanted to take a bit of a different bend with this talk. So I'm actually going to talk about some of the emerging issues and what we may have missed. And the reason I wanted to do this today is because through being involved with, since the first case of black lung in 2015, all the way through the silicosis cases, now one of the questions that's been asked is, how did we miss this, and what else may we be missing? And I wanted to go over some of those things. So we'll look at some of these other emerging risks. So some we're already addressing, such as welding fume and diesel particulate, while others like the engineered nanomaterials, the microplastics, some climate change related things, and critical minerals we'll talk about as well. And that's by no means an exhaustive list. Think of this more as a starting point for the conversations in some of these other things going on. And as you'll see from the timelines on some of these as I go through them, it can take a long time from the research being conducted to being declared a carcinogen to the exposure levels changing in legislation. And Bob alluded to this this morning too with the 50-year journey of silicosis in the US this morning. So I hope that this can start to raise awareness of some of these other issues so we can get the research started sooner, shorten the timeframes, and keep everybody safer in the meantime. So the report that's here is the baseline review of occupational health risks, and that was something that University of Queensland, so several of us in the MSHA group and Ernst & Young put together for RSHQ in 2021. And this does talk about especially some of the engineered nanomaterials in the risks there. Okay. So if you want more detail, check out the document. So I'll start with diesel particulate matter. So that was declared a class 1 carcinogen, as we probably all know, back in 2012. So the current standard's a 0.1 milligrams. And that's actually based on the irritant effects, not on the long-term health effects. So there was a recent Safe Work Australia WES review, and with that, they weren't able to determine a limit for the diesel engine emissions based on their normal review methodology. And as a result, a broader expert review was commissioned to determine if a safe limit can be determined. And we heard at last year's forum from Rob McDonald, who I heard online asking questions earlier from BHP on just how complicated and conflicting that some of that literature in the DPM exposure space can be. But from the latest update that Safe Work Australia provided to the AIOH, they will be recommending a 0.01 milligrams per cubic meter, and that's a 1/10 of what the current limit is. And this is based on respirable elemental carbon, and elemental carbon is a surrogate for DPM. And using the elemental carbon eliminates interferences from mineral dust, from cigarette smoke, from oil mists, which all show up in that total carbon fraction. However, interestingly, some of the control technologies may alter the relationship between the DPM and the elemental carbon fraction. And some of the DPM issues are also being solved by electrification and elimination of the use of diesel engines. But one interesting thing that's turned up in my work, as we know, coal also has a large elemental carbon fraction. And coal mines measure the submicron fraction of dust for DPM measurements with a cutoff of 0.8 microns. So in the past, I've talked about how I've found agglomerated DPM particles up to 2 microns in size, as well as DPM sticking to the larger dust particles where they may not get counted in this fraction. But since then, I've actually looked at a new scanning electron method, which takes the dust off the filter, puts it onto a glass slide, and this new method can see down to 0.155 microns, while the MLA, mineral liberation analyzer I've been using, can only see down to 0.63 microns. However, with the normal SEMs and what you've seen, some of the SEM work earlier in the piece, it only distinguishes a few major mineralogies there. And I've tried this with a limited number of samples, and so this mine in particular was very interesting. So keep in mind, the way we do DPM for coal is everything less than 0.8 microns is diesel, everything greater than 0.8 microns is coal, and that was just, NIOSH decided that in the 90s based on the data they had at the time. But as you can see here, your P50 is 0.72 microns, which means half of your particles are less than 0.72 in what's showing up on the filter. And this this sample is 82% carbon on that filter. So there is a large amount of submicron coal particles that would also be there as well. And that little divot in the graph there, that's at about 0.4 microns, that's actually due to the holes on the filter, because you need pores on the filter for the air to be able to pass through. So it's likely that this is actually an underestimation of the number of very small particles that exist in some of these mines. So that's going to be very interesting as we get into DPM for the coal mines. So the next one I want to talk about is welding fume. And so in 2017, IARC upgraded welding fume from group 2B, which is possibly carcinogenic, to group 1, which is carcinogenic to humans. And there are many different types of welding, as you can see on this lovely graph provided by the AIOH. So not all welding is created equal, and it can, the welding and thermal cutting fumes consist of very fine particles of metal oxides, silicates, and fluorides, and this depends on the composition of the metal being welded, of the wire, and or electrode, and any coatings they may have. So short-term effects can include metal fume fever, but long-term effects are numerous. So they can impact the respiratory system, nervous system, cardiovascular system, and also have carcinogenic effects. And internationally, there's a trend not to treat welding fume or metal fume as total dust. And initially, Safe Work Australia had recommended scrapping the total welding fume standard in favor of the individual components. But the most recent update says they are looking at a limit of 1 milligram per cubic meter there. But even with a total limit, the components are extremely important. And some of those proposed standards have come way down, some of them an order of magnitude for the individual components. But in some of the work we've done reviewing, hygiene reports across the country, we've seen people that are still just reporting total welding fume and not the metal suite in there. So it is very important to look at the individual components. Additionally, there's starting to be an increased concern over the nanoparticles associated with the welding fumes, as these might not accurately be captured on the mass basis. So the next one is engineered nanomaterials, or ENMs. And these are materials, as the name implies, on the nanoscale, with at least one dimension in the 1 to 100 nanometer range. And these materials often exhibit unique properties due to their small size, and they're intentionally manufactured. So really the only difference between nanoscale and ultrafine particles is how they're created. So we use nanoscale for the manufactured ones, and we talk about ultrafines for the naturally occurring materials. And there's a notable lack of documented cases and research on the human toxicity of the E&M exposure. And our understanding of the safety of it is very limited. And an uncertainty analysis that was performed has revealed knowledge gaps in some of the various aspects of environmental health and safety for these E&Ms. And so one challenge in assessing them is that most of them are small scale production, and the lack of data makes it difficult to predict the potential adverse health effects coming out of these. And additionally, we also have a rapid creation of novel E&Ms, and this is illustrated by the surge in the nanotechnology related patent applications. So this is a field that keeps growing that we know very little about. So the next one is the microplastics, and they have a whole range of things. And the research on this, I feel like that could be a whole own presentation on its own, but I'll just go over some of the respiratory health risks as part of this. But there's also a risk from ingestion and dermal contact. So these can lead to oxidative stress, inflammatory lesions, increased uptake or translocation, and chronic inflammation, as we've heard a lot about earlier in the day. They may also release absorbed contaminants and pathogenic organisms. And the immune system can struggle to remove these synthetic particles, resulting in chronic inflammation and increased tumor development there. And our knowledge on these, again, is very limited on the toxicity there. And it is influenced by various factors, including the exposure concentrations, the particle properties, the tissues involved in here, individual susceptibility, and further research is needed into this area. And they're released from various sources, such as synthetic textiles, the abrasion of materials, and through resuspension. And the size and density of these particles can influence their deposition into the respiratory system. So the next one is climate change. And I pulled that first article, that was just Monday. Apparently it's gotten a little bit better now that it's cooled off, but we are in for a big fire season this year. And the newspaper headlines, typically tell us about the casualties, the displacement, people losing their houses, and sometimes even the mental health concerns about these natural disasters. And there's good advice about some of the acute exposures from bushfires out there, but there's actually very little on the long-term health effects. One of the few places that's actually done a really nice job on this is the Hazelwood Health Study. So if you're not familiar with that one, in 2014, there was a bushfire that ignited old exposed workings of the Hazelwood mine in Victoria. And there was about 100 meters of brown coal exposed in that high wall, as well as vegetation that had built up around it, which fueled the fire. And so the Hazelwood mine's located about 400 meters from the township of Morwell, which has a population of 14,000. And the fire there kept burning for 45 days. They did evacuate the vulnerable people from the town. And there was, as you would expect, a surge of respiratory illness as a result of the fire. But the more interesting thing is that because of this, they commissioned a longer-term health study. This is by Monash and the University of Tasmania, and that's actually now in its 9th year, which has some great data on the medium and longer-term symptoms. So for instance, they found that in children 3 years after the fire, there was still some stiffness in the lungs and blood vessels, but this had resolved 6 years post-fire. But in adults, they still found an increase in respiratory symptoms 2.5 and 3.5 years after the fire, including cough and shortness of breath. And that's talking about the communities around, but we also, as I had a great conversation with Keith in the break, that the fireys here who are going from one fiery to another and dealing with some of this. And I was back in the US recently, and I think every third commercial was a class action lawsuit on the PFAS, or the firefighting foam. That it's a very big thing over there right now. So, you know, another issue to add to that. The next one I want to talk about is actually the critical minerals space, because I think this one's going to be a very interesting one. So industry and government are working to fast track the extraction of these minerals, but we may not fully understand the health hazards associated with them or new mining and processing methods that they'll require. Another factor to consider is that most of the exploration and mining in this space is done by juniors, so smaller companies who may not have the resources or expertise around some of the health and safety aspects. And this has been brought up twice before, this morning by Bob, talking about the small mines as a risk factor for silicosis, and then Stephen as well with how the tier 1 companies are doing versus some of the smaller ones in the silica space there. Yeah, so just the size of them is a factor there too, and some of the unknowns. So lithium, for instance, is often in spodumene, which is an aluminosilicate, and likely also contains silica. It can also be in white micas, such as illite, which are known to be high in potassium. And as we learned last year from Basil Beamish on the work that he's been doing with Graham Zosky at the University of Tasmania, they found a correlation between the potassium levels and the cell death in the cells. And we think that the illite that we're dealing with in the coal is potentially also the same that we'd be dealing with in some of these mica deposits. And some of the, just anecdotally, some of the geologists working with some of the core samples have told me that some of these are very friable and easily turned to dust. So that one's actually Canadian, but couldn't find any good Australian ones online, but that gives you an idea of just, you know, how much some of this stuff breaks up into. And so for some of these other substances, we don't have good handles on the exposure limits. Even for lithium, SafeWork Australia has one for lithium hydride, but that's normally a synthesized product in a laboratory. There's none for the lithium carbonate or lithium hydroxide that are normally produced as part of mining. And there's only a few global limits set. So Germany and Switzerland have an 8-hour TWA of 0.2 milligrams per cubic meter. And then Canada and Japan have a STEL for it of 1 milligram per cubic meter. Another interesting one is vanadium, because there is a number of limits set, and they're actually very low. And this is one of the common vanadium compounds produced through mining and processing. And so some of these limits range from 0.005 to 0.05 in the respirable fraction, and between 0.03 and 0.2 for the inhalable fraction in a number of countries. And so these are just two of the main critical minerals there, but there are many more. And for a number of these, we don't have the history or the research because of the small number of them or where they've been mined to have a good handle on the exposure limits and the health effects. So this is definitely an area where we need more research. So with silica, I have done a good bit of work with the silica through the coal mines, and the three photos you see there are actually from the mineral liberation analyzer. So it is a scanning electron microscope, but this has the benefit of actually being able to get the mineralogy. So the bright yellow that you see is silica, and I can get a false color map of all of the individual particles. So the top left, that particular mine, so there was a lot of the black is the carbon that encasing some of the particles. The bottom, actually that would be your right, is a lot of those are aluminosilicates surrounding those particles, and the smaller one is many more just pure silica particles. So even just talking about the silica and the particles there, like not all silica is created equal. So you know, what they agglomerate with can affect the health hazard of them. and the size plays an issue in that. So I am actually recruiting stone bench tops for one of the current projects now. And this would be to go out into the workplaces and actually look at what's being generated in real time by the various equipment. So if you're interested in participating in that one, there is a QR code there with a participant information sheet that you can get in contact with me. And I'm also interested in looking at the new low silica products to help ensure the safety there, being able to look at the size, and the MLA has the ability to actually look at the mineralogy of the other particles as well. And that wraps up my presentation. So thank you for listening to some of the new emerging risks out there, and some of the not so new ones. And I would be interested in hearing, more thoughts about what else you see as emerging risks in the space to help shape the research going forward. And while I'm up here, I'll take off my presenter hat and put on my forum organizer hat. And announce that next year, for the 7th annual Dust and Respiratory Health Forum, we will have that Wednesday, the 30th of October. So, which will be the week of SWAT back here on campus. So, but Wednesday, not the Thursday. So I do hope you can join us for that. I would like to thank all our speakers today. If we could give them a round of applause. Thank you. And I would like to thank our sponsors as well. So to Breathe Safe and to RSHQ, thank you very much for helping make this a possibility. And the event will be recorded, so we expect to have that up sometime next week. And we will send you an email when it is ready and that recording is posted, so you don't miss it. Okay, and now we'll open it up for questions for the speakers. Questions, anybody?
Do we still have Chandnee with us?
Yeah, she's back there.
Can't see her. Because we had a couple of questions we didn't get for her. For her. She got a microphone or coming down or?
Can we hold that one and we'll let him ask his question and then we'll get it to.
Yep, no worries.
Go ahead.
Yeah, okay, thank you. It was a very good day and very interesting and I enjoyed it. My question is since the standard of pressurising our cabins, which we've done at work, and as a maintenance type person, I do see the notice that less dust in the cabin space from these pressurised units, which are monitored. Just the question is, it seems like the people, and one of the problems we have at the mine I work at, is that the people on the ground outside of the pressurised cabs didn't seem to get a sort of mention or that in the last standard that was brought out that included the Breathe Safe. And I just wonder if any of the speakers had any sort of ideas on something that could help us with managing what sort of triggers might act to help these people who are on the ground outside of the air-conditioned cabs.
Any of that
Hauntiness, yeah.
I'll have a crack at that. So I'm assuming you're talking about recognised standard 20 for controlled dust in surface mines. So there's a whole range of elements in that look at operational controls, not just the maintenance controls for enclosed cabins. So there's work on dust suppression, there's work on mine planning. There's a whole range of elements within that standard or to cover off sort of all of those other people that work outside. So there's specific elements in there on like blast crew. So planning work on blast patterns and things like that. So there's a range of other elements in that. you can get hold of that standard just off the RSHQ website. So, yeah.
It's just like we monitor, we've got our 50 kPa of pressure in the cap, we've got a real-time monitor. What that pressure is like in the cap and what the conditions are. A little bit harder when we're outside.
Yeah, I understand. I completely understand. Yeah, it's, you know, the other aspect that potentially you can use is, you know, like personal, you know, real-time instruments, you know, like the little ones that you can carry around that, you know, that may set an alarm or something like that to it's like a short-term alarm or something like that, where they can go, okay, I'm working outside the cab, I'm doing some work, you know, on the drill or something like that, and then if I get a peak over a certain limit, then okay, obviously our dust controls outside aren't working, so maybe we need to, you know, get something else.
Do you know what the level would be?
Off the top of my head, no. You know, it really can come down to, you know, what the site decides in terms of, you know, what's the level, what sort of tolerated level. You can go with, you know, like 3 times. You could use it like 3 times the exposure standard as short-term limit. You know, there's general guidance on excursion limits in safe work, sort of their guidance on short-term exposures and things like that. But yeah, there's no, you know, 15-minute limit for silica or anything like that. Yeah.
You touch upon an important issue that, and we've covered it indirectly during the course of today around the exceedances and the excursions from the exposure limits that are currently in play. Now, one of the things that I would comment on is that in all the medical literature that I've looked at, you know, I haven't seen any cases of silica dust or mine dust related disease associated with circumstances where they were compliant with the exposure limits of the day. So it's not the exposure limits or the action points associated with those exposure limits. It's understanding that this is a nature of the hazard that you're exposed to. And we're using these exposure limits as a surrogate to trigger safer work practices. Now, the goal is to actually have you going to work and coming home well. It's not going to work coming home sick, which is the current situation given the framework that we're looking at. So excursions, exceedances to exposure limits, what's the appropriate exposure limit? Why do we have an exposure limit? It's to trigger action. Is it the end of the solution? No, it's not. Chandnee?
There just was a quick question for Chandnee around the samples that she analysed of engineered stone, both the old style and the new engineered stone products. So Joanna Holland was interested in knowing whether the safety data sheets that you were able to obtain for those samples, if they accurately reflected what you found within the samples, particularly with regards to things like cobalt, aluminium, the resin and the silica content.
That's a great question. I think the short answer is no. There's just not enough information on the safety data sheets of these engineered stone products. There is a paper out from our research team that was led by Professor Pisaniello that's available online, open access as well, that talks specifically about the lack of information in safety data sheets regarding to these products.
Stay there. There's one more question for you. Shella-san wanted to know how you generated the dust when you were cutting the engineered stone products that you then sampled or were analysing. So she wondered what the cutting method was that you were using.
Yeah, again, there's a bit more methodology in the papers published, but we were basically trained by stonemasons, but obviously in a very safe environment to do zip cuts through the stones in a very similar way that they will be doing cutting. Particularly, we have undertaken some other tasks as well, like polishing, but our main focus was on cutting tasks because literature has shown that those lead to the highest exposures to respirable crystalline silica. So it's zip cuts.
So we've got a question from the middle of the room. I've got one over here and then there may be another one online.
Again, Dr. Chandnee, I was just wanted to ask a question about the methodology. I've seen your paper before online, actually. With the cutting chamber, and given that industry mainly uses dust suppression, water on tool techniques, did you do any sampling or did you do any testing using that water tool on dust suppression? And what sort of results did you come from that?
Thank you. Yes, again, a question that I get very often. Look, the design of the methodology was fit for purpose, given what we wanted to find out. It was enough. Doing some wet cutting was not enough to capture enough dust to really understand the depth and the breadth of the characteristics. Although, mind you, when the first program was set up, it was back in 2018 and dry cutting had not yet been prohibited in Australia or specific jurisdictions. But to answer your question, yes, we've looked at some of those, and I'm happy to share some paper. I think Associate Professor Sharyn Gaskin presented some research last year at the IOH conference where we undertook wet cutting and wet polishing and looked at respirable dust concentrations and respirable crystalline silica as well. I think overall it's just much lower concentrations as you would expect. But some of the really interesting findings were brief, high exposures despite the wet cuts, as we've seen in workplaces as well.
Can you use the microphone, please?
So online can hear you.
My apologies, people. That actually correlates with some of the stuff they've actually seen real time in the field where we've done dust monitoring. There was a gentleman who was actually cutting a footpath concrete with a quick cut saw, had the water suppression on. The respirable dust levels come back low as expected, but he had exceedance on RCS. So we were trying to work out what the story was there, and I proposed that it could be that the tip speed of the blade itself is actually generating very fine water particulate, and that the finer particles, like the RCS or like the very fine respirable dust particles, they are being carried in the water particle into the sample head. And when it flashes off, it actually leaves that particle behind as deposited. It could be that it actually makes it more sort of like bioavailable, or as a better transport system to actually bring it in further into the base of the lungs.
Yeah, that's true. We've seen very similar things when we did some field work as well. And very often it was as simple as using, even it was a wet cutting tool, the direction in which the water jets were hitting the blade meant that not all the dust was being suppressed. And we've got like really great pictures and real-time monitoring and levels of dust and respirable crystalline silica to give that exact snapshot. I'm happy to share at a later stage. Thank you.
Thank you. It highlights that not all water suppression is equal.
Very good. Thanks. This is a question for Kate. Just with regard to your presentation. Thank you very much. It's a nice question. It's okay. I know that you did a lot of work and you were fortunate enough to travel and see quite a lot of international tunnelling operations with your Churchill Award. Congratulations on that earlier, a couple of years ago. Where do you think we sit internationally with regard to current best practice and controls in Australia compared to what you've seen internationally?
Thank you for the compliment and the difficult question that followed. Look, when I did my Churchill Fellowship, I went to Norway, the UK, the USA and Switzerland to look at the tunnelling epicenters of the world. And I think what was really sad to me was that I saw safety practices there that were pretty abhorrent, and I was really proud to be Australian. Like, the safety practices in Australia are amazing. But then their health practices were like orders of magnitude better. And I was thinking, wow, okay, how can we be so good at safety and so poor on health? And where we are now, I'm fortunate to sort of as an independent consultant get across to a lot of different tunnelling projects. I've seen some great things. Like, there are some really great projects doing amazing things that have absolutely invested, very large companies doing the right thing. That's very good. The challenge is we can't judge the industry by the best. I wish we could, but unfortunately we can't ignore the worst. And the worst is still bad. It's really not that much better than where we were 5 or 10 years ago. And the challenge so much is the makeup of the industry. There's a lot of subcontracting, there's a lot of smaller contractors that will come in and service tunnelling projects. It's not just 1 or 2 or 4 companies we're talking about. We're talking about an industry that's very diverse. And the photographs I showed in my presentation of those really bad engineered stone work, that really bad series of engineered stone workplaces, you know, that photograph was taken last year. And I could equally show a photograph of what looks like a good engineered stone workplace. All tunnelling is the same. It's very diverse. So how does it compare to tunnel projects I've seen internationally? They still do a much better job internationally. Occupational hygienists and occupational physicians work really closely. They have mandatory health monitoring and screening practices that are better than ours. They have mandatory reporting of exceedances. They have mandatory dust monitoring. They have mandatory controls. And it's a culture, which is very different to our compliance culture that we generally have in Australia. So we still have a long way to go.
We'll go to the online questions now.
So these are for Kate. So Faiza, you want to give Kate a microphone?
Sure.
All right. So first of all, Alan Williams wants to know about ventilation in tunnelling. So one of the key differences between mining and tunnelling is the ventilation design. Are you aware of any work being done in Australia or internationally to redesign and improve tunnelling ventilation? Because as you say, this type of work could or would not be done on, you know, shorter length projects or individual projects.
That is an excellent question. And the number one thing that fails in tunnels under construction is the ventilation. So poor ventilation, poor health outcomes generally. So in New South Wales, we had a code of practice before the harmonised work health and safety regulation. A code of practice is like from 2006. And it has a ventilation criteria in there of 0.5 metres a second. The Safe Work Australia guide, which is obviously not enforceable, that suggests, I think, 0.3 metres a second. Tunnelling is not like mining, where we have criteria. There's no criteria, for example, for a full-time ventilation engineer. I can hear the miners gasp. There's no criteria for daily testing or that testing to go anywhere. Again, I can hear the miners gasp. So it is a huge gap. In terms of what I'm aware of, I do know that Transport for New South Wales is in the process of developing a standard for the construction or the design and construction of temporary tunnel ventilation in New South Wales. And that is a very welcome initiative that they're currently undertaking, because unless we focus on the engineering controls in tunnelling as a critical control and then the associated testing and maintenance of that, we're really missing the big picture.
Thanks, Kate. Another question for you from Shane Power. Are you looking at the workers who make the prefabricated concrete sections of the tunnel, or concrete workers in general as part of your PhD research?
Yeah, so my research covers everything that involves all workers that are involved in a tunnel construction project. So we know that workers, particularly on projects like tunnel boring machine or TBM projects, need to manufacture precast elements or the rings that put the tunnels together. And in some circumstances, those rings or concrete segments have needed to be grinded in order to achieve QA/QC compliance. And that grinding should be undertaken with HEPA extraction or wet tools, and isn't always, or even better, there's better safety and design processes to eliminate the need for grinding. So it does cover that, and that is definitely an area where we do see exposures of the exposure standard in an above ground context in tunnelling if it's not adequately controlled.
Thanks, Kate. The last question is a general question for any of our speakers who can answer it, which is, has anyone done a study to determine how much dust exposure comes from dust producing activity like cutting engineered stone versus how much comes from residual dust on the hands when touching the face or on the PPE, or when handling the products later, or even at the laundry later in the day?
I'll probably be able to answer that one. No.
There you go. Whoever asked that question is a PhD for you. I just want to very quickly thank the people doing the microphones today. So Faiza, Husna and Sistia are UQ students here studying OHS with us. And we've also got quite a few of our students that have been in attendance today. So this has been a fantastic learning opportunity for them. So thank you, Faiza, Husna and Sistia for volunteering.
I'll hand back to Nikki to wrap.
Any other questions? No. All right. Well, thank you everybody for coming. I appreciate you all coming out and being here, and it's great to see so many faces now, and I hope to see you next year back here again. So please enjoy the afternoon tea. Thank you.